Okay, hello everybody. We are about to start a working session for Wolfram Physics Project, and today's topic is quantum computing and its relationship to our project. And Jonathan here has hopefully got some interesting things to show in the effort to compile our standard, quote, standard quantum computing framework to our physics project multi-way system way of reproducing quantum mechanics. So Jonathan, do you want to go ahead and share? Let me unshare and
If that's
go
okay.
ahead and
Thank you.
go ahead and do your thing. Let me just actually, I'm just going to do something here to prevent something getting confused here. Okay, go ahead.
All right. Okay. Can you see? Oh, sorry. There's a thing on my
see
side.
a screen. Yeah.
Yeah. Let me. Oh, no. All right. That'll have to stay there. All right. So just the okay. The most elementary thing we can do is just take a specification of a quantum evolution, which in our quantum computing framework is given in the most basic form by an operator and a basis. So if we take something like a Hadamard gate, which has this matrix, and we say it's acting on a basis given by the identity matrix of dimension 2, then we can just immediately compile this to a collection of multi-way rules. And then, so then if we take
Wait a minute, how hacky are those? Are those strings in some way?
Yes. So
can
quite
you do
hacky.
an input form there just to show how hacky it is? Okay, that's very, very hacky. Right. You know, let me make a suggestion that if we're really going to do it at this level of hackiness, why don't we embed some other CRUD in the string so that you can see that it isn't actually the list 10?
Sure. I mean, I was going to do it with kets and things, but then
oh, that would be beautiful.
I didn't. Like obviously, it's important to stress this is only temporary, because of course once the actual QC framework is live and people can use it, then we'll have actual quantum state objects here, purely symbolic quantum state objects.
And that will work in the multi-way systems.
Yeah, absolutely. It's just that we can't put that in the function repository as is because it has a dependency outside.
Okay. All right. I get it. But okay, fine. All right. Let's keep going.
Okay. So if we take the specification of this multi-way system and we say, okay, let's start from an initial state 1, 0, and let's go one step and show the evolution graph, then we can see what this Hadamard gate is doing. And so if we do 2 steps, it'll do something a bit more interesting. And then we can say include state path weights, true, and then we can say vertex labels, vertex weight. And so now, now we can compare this against...
Hold on, you're going too fast for me. Okay, so what we're doing here is we're starting off from a quantum basis state 1, 0, right? And so we could start off from a superposition of states there.
Right. In fact, let's do that because that'll be more interesting. Let's start off with what superposition do you want?
That plus square root of 2 times. No, I can't do that. I've got to have an integer, right? So
right. We can approximate square root 2.
Yeah, well, let's do just 0, 1, 0, 1. So in other words, 1, 0, and then 2 0, 1, 0, 1s.
Okay. Like this?
Yeah.
Okay. So that's what that evolution will look like.
Okay. So let's just understand exactly what happened here. Okay. So this is... Okay, so in the standard quantum way of doing this, we would be getting... The only difference here is that the minus sign is being encoded through another state here.
Yes, right. So although in principle, what we want is actually, to get the actual destructive interference between states, which we should be able to do when we have a more general way of representing measurement. But until then, it's helpful to actually coordinatize these things, which is a bit of a hack. But
so I just a super practical question: Did Ruhi join us or not?
She did not. I can ask her quickly if she's once I'm off sharing.
Why doesn't somebody else see if she's available?
Okay. Right. Anyway, so if we compare that against the actual sort of evolution for that, the matrix evolution, you can see. So the answer we should get. Oh, sorry, hang on. This was 2 evolution steps. So I should do matrix power. That's 2. So what we should get is 2, 4, which is actually what we get, right? Because we have 4 of these 1 zeros cancel out with 2 of these, and then 5 cancel out with 1 of those. So that's all unsurprising. And it's worth mentioning, I don't think we're going to use it as much, but if we want to, we can go the opposite way around. We could say, if we have some multi-way system like this, I don't know, this is a boring multi-way system, but we could always do that. And we can compile any arbitrary string multi-way system, or actually any arbitrary multi-way system, back to its analog as a quantum operator.
Let me see that for a second. Okay, just give me a Fibonacci. I mean, the strings have to be a fixed length. Is that correct, or do they not have to be a fixed length?
So if you want ordinary, if they're not a fixed length, then of course you've immediately got an infinite basis. That's the only slight complexity.
Why?
Because your basis vectors are, the number of degrees of freedom in your eigenstates is increasing.
So you're doing quantum field theory.
Yes, right, and that's a case that I haven't yet.
But that's not an uninteresting. I mean, that is an interesting way of thinking about, for example, the ladder operators of. I mean, even the creation and annihilation operators.
Absolutely. So I think, yeah, I agree. I think Fock space is well formalized as effectively a growing string multi-way system or something like it.
Well, how clean. That's really nice, if that's right. I mean, because Fock space is usually a huge, horrible, complicated mess. And that's an much easier way to understand it. That's cool, very cool. Right. Okay, let's try to remember that. Somebody needs to take notes about this. Let's make sure that your notebook here is.
Yeah, I'll save this out.
Right, save it to the working. But I'm going to make a note separately. Okay, make a heading. Yeah. Okay. Right. Okay. Cool. All right, let's keep going here. I mean, it is interesting to me to know, and we'll do that when I'm because I know how to operate those enumeration, substitution system enumeration things. I'd like to see what the simple substitution systems correspond to in terms of quantum gates.
Yeah, I agree. That's going to be super interesting. We should do that this session.
Okay.
But yeah, so this is a totally boring. Yep.
Can you explain again where 2,4 comes from?
Where what comes from?
Where the 2 and 4 comes from. You're subtracting. These states are the kind of mirror states.
Yeah, 4 minus 2 is 2, and 5 minus 1 is 4.
Yeah, makes sense.
Okay, so then and this is a completely boring example, but this is telling us that if we took AA and we apply this rule, we get AA, we get AB and BA, which we kind of knew. So we could, I think we can even do this.
Okay.
Oh no, wait, I forgot how this works. No, I need to double check exactly how that function works. But okay, right. So let me now show, because I just wanted to kind of illustrate exactly how measurement works and what exactly it is we're trying to determine, and then we can go back to you sharing.
Okay, so I just want to talk for a second more about the negative states here.
Yep.
And whether we see those as being actually the other ends of geodesics, or how we think about those.
Yeah. Okay. So here's the real point, right? So actually, right, this is not because these have non-trivial state path weights. If we do, is it evolution graph unmerged? Right. So if we did something like this, this is the real thing that we're actually operating on, right? Where all of the states are actually unmerged. And so in that case, it's reasonable to say that in branchial space, the 1 zeros on this side are canceling out with the 1 zeros on that side. But because we don't yet have a generic way of representing that without coordinatizing.
Wait. Too fast. Wait a minute. What 1 0? Why? I didn't understand that.
Okay,
so
hang on.
This is I understand why the path weights. What did you just do?
So I made this a simpler system, so it's a bit easier to see what's going on. So here's an example, right? So here's a 1 0, here's a 1 0. Right, that's the kind of thing that could happen. And so what we actually want and what will be the case generically, when we have a way of doing sort of coordinate-free measurement on branch yield space, which I'm working on, a geodesic going in this direction and a geodesic going in this direction will be at 90 degrees, and so when we do a projection, they will go to 0.
But wait a minute. But they're both winding up at the same point in branch yield space. 1, 0 is 1, 0, and that's a certain coordinate position in branch yield space, isn't it?
No, because so it is if you coordinatize, like, which is what I'm doing here. But if you don't coordinatize, every state is ending up at a different point, which is why you can get the effect of destructive interference.
No, but the destructive interference is coming because you've got those 0, -1 states, which are representing going to a different position.
Yeah, that's my point. The 0, -1s are fakes, right? They're my coordinatization to deal with this problem. In the true physical case, there is no 0, -1. There's only 1, 0 and 0, 1.
Okay, let's go through this another time here. Okay, so hold on. So the claim is every branch pair, we can think of every branch pair as being at 90 degrees in branch yield space. That's our first approximation. Okay?
Right.
And then some branch pairs land up in states that are on sort of opposite sides of branch yield space.
Yes.
Some branches of those branch pairs. Okay, now we're asking the question. So when we make a measurement, what we're fundamentally doing, a typical measurement is fundamentally picking a quantum observation frame that samples a particular part of branch yield space.
Right.
And what you're saying is, if those things were at 90 degrees, then they shouldn't land up in the same part of branch yield space.
Yes. Right.
But nevertheless, I'm a little confused because the labels that we're using, let me just remember what this is really going to be like. So in the real case, these are not strings, but they're hypergraphs. So what we're saying is there are two identical hypergraphs. I don't understand that. I mean, there are two identical hypergraphs that land up at different places in branch yield space. What does that mean?
I mean, it's an indication that so in the unmerged case, it's an indication that they had very different, that at every stage they emerged from a different branch pair.
Right, I understand that, but the fact
in
that
the
they
extremal elements at every point.
Are you claiming that our usual merging by isomorphism, by hypergraph isomorphism, is not ultimately correct for this unmerged branch case?
For understanding destructive interference, I think it is not as useful as considering the unmerged case.
Because basically what we're having to do in the case of multiway systems, okay, so your claim is there are path weights. Okay, so let's remember what we're doing in coordinatizing branch yield space. There are two different things. There's the path weights, which are giving us the magnitude of the quantum amplitude, and there's the position in branch yield space, which is giving us the phase. And what you're asking, so what we really want to do is we really want, when you're tagging a 2 there, right? What's the mistake is the 2 being is the tag of 2 there. And someone is asking on the live stream, and there's several other questions which we'll come to in a minute. Why is there a 0, -1 in the uncoordinatized example? Yes, it's kind of a fake, right? That 0, -1. What we really should be doing is to say that the 1, 0 down in that second example.
This is a coordinatized example. These are all coordinatized. This function is coordinatized. That's my point.
Okay, but a different way to think about it would be to say, let's measure where in branch yield space. So we know the path weight, right, which we're going to get from. I think this is the way to think about it. Okay, so every time we make a branch pair, right? Yes, this is a way to think about it. We've got a path weight. Every time we make a branch pair, where that's generating a new path. Okay, it's also generating a phase by virtue of the fact that it branched, that the branch pair should both have, they have different path weights and they have different phases, I claim.
Yeah. Mm-hmm. Yeah. Right.
And so,
and so the point is, it's no longer sensible to think about it. If you're trying to think about things in terms of phase and amplitudes, then the merging operation makes less sense, because then things.
I agree, because we wound up with things of completely different phase being merged.
Right. Exactly. And in particular, things like sort of the trivial critical pairs, right? The situation where both elements of the branch pair happen to be identical. Those are important for deducing amplitude and phase, but of course they're ignored in the merged model.
All right. So what if we were to make the phase? If we were to indicate the phase, so remember the magnitude is coming from path weights, but the phase, every time you are making a branch pair, you are effectively, what the heck are you doing to the phase? Because it's kind of complicated, because you're in high dimensional space in this branchial space.
Mm-hmm.
So how should we think about that? So you've got 2 points that are coming out and going unit distance, right, in a space of any number of dimensions.
Mm-hmm.
And those two things are supposed to be orthogonal in that space.
Right.
Right. So we could almost, I mean, it's a bad way to think about it, but we could almost think at random. We're in d-dimensional space, and we take these branches, and they're at random going in, unit distance orthogonally in that space.
Mm-hmm.
Right.
Right. It's almost like it's like one of those causal set percolation models, but for Hilbert space.
You're too fast for me. Hold on, let me think about that. You're saying,
you remember when those transitive percolation things?
Yeah,
where
no, I remember
you're
those,
constructing
yeah.
a post set by just randomly picking sort of
I see what you're
picking partial order relations to by adding elements to the post set. If we do the same thing, but not with space time, but for some kind of Hilbert space, I think that's essentially what you're describing.
Yes, except that we don't want that. But the issue for us is, okay, so the true answer, the true way this is being set up, is those coordinates are actually defined by the branchial space, basically.
Exactly.
What we're doing here, but let's just think about how we would do that. So you're making. Okay, so the issue is really this. I mean, imagine we had a hypergraph, and I suddenly started saying to you, what are the coordinate values of the elements in the hypergraph? You say it doesn't make any sense. They're just that they're all we know is relative information and geodesic balls and things like that, right? But for conceptual purposes, we are drawing the thing. Okay, so here's the way we should think about this.
Yeah, this is like an embedding.
Right. For conceptual purposes, we are drawing this thing. So the way we should be drawing this is actually with things at 90 degrees, right? Because if we could do that, right? So in other words, unfortunately, we only live in three-dimensional space, so far as we know. So we don't get to do that as well as we might. But essentially, what we're doing conceptually, I mean, in the hypergraph case, the relationship of elements in the hypergraph is conveniently represented for us humans by doing, the embedding in two-dimensional space or whatever. Okay, so now the analogous thing here is we want to, every time there's a branch pair, it's quotes 90 degrees in branchial space.
Right.
Okay. So the question is really, if we were to try to draw this thing so when we draw a hypergraph, what we're trying to do is we're trying to make the embedding in physical space, in our drawing space, be as faithful to the graph distance as possible.
Right.
That's the goal. Okay, so what is the similar goal here? We would like it to be the case that in phase space, by phase I don't mean ordinary phase, I mean the phase of the quantum amplitude, right?
Yes.
In quantum amplitude phase space, what would we like to have this look like? We would like to have it be the case that what would we like cancellation to look like, basically? So would we like it to be on the surface of a sphere, for example, that we're basically putting, we want a faithful embedding. What does a faithful embedding look like? A faithful embedding presumably looks like we have a combination of identical states, and they have wound up in different places on the sphere. And to find out the net value of one of those states, we take the average of, or maybe it isn't even a sphere. Maybe it's just, maybe you can just do it on a line, and it's just asking, or maybe it's a circle. Not sure. But you get what I'm saying.
For the qubit case, you can do a faithful. The concept of a faithful embedding into the block sphere would be an embedding in which the perpendicular things that should cancel out become the antipodal points.
Okay, fair enough.
I think.
Yeah, fair enough. So you're saying that the ultimate embedding is onto a circle. So
or yes, some end sphere for a more complicated system. Right, because I mean, the block sphere for this case is just you're unwrapping this so that this 90-degree angle becomes a 180-degree angle.
Yes, so I understand. So you're saying the canceling phases are going in opposite directions. So in other words, if we were to do this as a tree embedding, if you were to just take that graph, and why don't you do it? Why don't you say tree plot of that graph, comma center?
Cool.
Okay.
It's a weird block sphere.
Yeah, right. So now let me just understand. So what we're trying to do, I mean, this is an important kind of concept here. We understand how to map hypergraphs onto something which approximates physical space and allows us to understand, the correspondence between the hypergraph, between space in a hypergraph and space in our physical experience. Mm-hmm. We are less familiar with quantum space, so to speak. So but what we want to do is to map the structure from the multi-way system into something which approximates, the world of quantum phases.
Mm-hmm. Right.
And the reason we're doing this, so Brian is asking what is phase in branch Hill space, but basically what matters is the turning of GD6. So as we, that's what determines the weighting of a particular state. In other words, let's give an example. Let's say you're doing an S matrix and you have an initial state, which you've prepared an initial state which corresponds to a certain location in branch Hill space. Then the question is, what is the transition amplitude to a final state? And do you hit the right final state, if you understand what I'm saying? And you don't hit it if your GD6 turned in the interim. That makes sense? And so phase, so what we're trying to work out, and if you had multiple GD6 all trying to reach, see, this is the part that I'm a little confused by. You have multiple GD6 trying to reach one quantum state. Mm-hmm. And they're at opposite ends, and those GD6, I am confused here. Okay, so those GD6 wind up in different places. Walk me through the issue of isomorphism versus, I mean, because like saying GD6 in, connections in the hypergraph that go to the same element. They may take different paths, but they get to the same element.
Right. But in the hypergraph case, just as in the branch Hill case, we can't, in order to be able to take a definite continuum limit, there are two averages you have to be able to take. You have to average, you have to do some smoothing over the actual GD6, right? You can't just consider a single GD6. But actually, if you want to recover a Riemannian metric, you also have to average out over the initial and final points, right? You have to grow out a finite GD6 ball, and then you have to ask what's the average distance between between one point on the first geodesic ball and the corresponding point on the other geodesic ball.
Okay, so you're claiming that when we try and take the continuum limit, we will be combining effectively these geodesics, which are in fact separate. They in fact deliver two hypergraphs to different places in this space.
Right, but they will be sufficiently close in branch Hill space that you'll be able to grow a finite geodesic, I don't know if the right term is ball, but a geodesic whatever, in such a way that you can do the same construction as you would in the hypergraph case.
Hold on, let's walk through that. So you're basically claiming that in trying to take the continuum limit, that you would have to aggregate these geodesics that delivered the 1, 0 to different places.
Mm-hmm.
That's your claim.
Right.
That, in other words, or put a different way, I
mean, you remember this issue when we were trying to define sectional curvatures in hypergraphs, right? So to do that, you have to basically specify 2 geodesic directions. Then you have to sort of consider the same 2 geodesic directions, but displaced a bit to simulate parallel transport. And then you have to work out what are the average geodesic distances between those 2 geodesic directions, but in those 2 different places. And you at the time, I was at the time thinking that you could just do that by considering only a single hyperedge as your unit geodesic. And you made the point that turned out to be correct, that you couldn't do that. You had to consider a finite length geodesic to make that construction work.
Yeah, well, let me see if I remember that. This was in connection. This is in connection with the angular momentum stuff, or this was a different thing?
No, this was long before. This was after. This is sometime earlier this year when we were talking. This is after the conversation with Isabella. We were talking about sectional. We were still working out the details of the GR derivation.
Right. Okay.
And so I had some model where unit vectors were going to be single hyperedges, and you.
Oh,
said,
yeah.
That can't possibly work.
Yes.
Right. And the reason it can't possibly work is because in order to be able to have a well-defined continuum limit, you have to have things of finite extent if you're going to measure distances.
Yes.
So you have to smooth things out. And so that's what we have to do in the hypergraph case. That's why we can consider when we take distances between 2 points, yeah, fine, we can approximate it by a single find shortest path. But in reality, you have to grow 2 finite-sized balls and then measure average distances between points on those balls.
All right, so let's understand the branch hill analog of that. Okay,
Mm-hmm.
So what you're saying is, I mean, well, the two overarching points here. One is I want to figure out how we get a better visualization of branch hill space.
Right.
Which is not going to be trivial because it's Hilbert space is hardly the world's most visualized thing.
No, yeah.
In fact, I don't know of any reasonable visualization of Hilbert space
other than block spheres.
Well, how reasonable is that? I mean, that's good for 1 degree of freedom, but it's not. It's what do you do for a 10 qubits is a 10-dimensional block sphere or something?
Right.
Then where are you? I mean, I don't know whether you can unroll that. I've not seen that. Is that a thing that people, in the quantum computing literature, is there a reasonable?
People have tried. It doesn't really work, in my opinion.
Well, so in other words, when you show the evolution of a quantum system, a 10-qubit quantum system, you could show it as sort of a cellular automaton-like evolution, showing sort of the densities on block spheres.
Well, that's effectively what that paper that Ruhi and I wrote was doing, right? To simulate the evolution of a large quantum system, you split it up into a tensor product of individual block spheres, and then you plot densities on the block spheres. That was the.
Does it look reasonable?
It looks as reasonable as a CA does.
No, but it doesn't look as reasonable because it isn't local, is it?
It is. Well, I mean, for that particular system, it was, but in general, it wouldn't be. Or your neighborhood structure would be the entire register, which is not
because the unitary matrix, the unitary evolution matrix, if the Hamiltonian is local, the unitary evolution matrix is not, is it?
Yes, right. I mean, we were considering only we were considering compositions of local unitary matrices. So we got around that problem, but I agree in general that's not going to happen.
All right, okay, but so one of the issues here is the conceptual visualization of branch hill space involves what we're trying to do is for each degree of freedom, each branch is going opposite directions in block sphere space, so to speak.
Mm-hmm. Right.
And like that next picture. So now, actually, that picture isn't correct either because I mean we have to have another dimension there to go.
Yeah, right. I mean, so in this case, this is the second dimension here. No, wait, which is the second dimension?
No, it's just
this is the second dimension.
If you do tree plot 3D, it might work. Try it. Oops, there isn't a tree plot 3D. Or try tree plot, and then try graph 3D of that. No, that won't.
No. Is there a? Hang on. Is there like a tree embedding?
3D, there is a tree embedding.
You know what it's called?
No, I don't. Centered. It's called center something or other. Look, they just press the down arrow at the bottom of the autocompleter. start and try radial embedding. Try radial embedding.
Okay.
Hopeless.
Star embedding.
Try it. Hopeless. Don't know what it is. Okay, but we should be able to get all
right, we can look into that. But I should mention, by the way,
if possible, you need to remove coordinates from the graph.
There are no coordinates. I mean,
yeah, there are no coordinates that
the states are coordinatized, but nothing in the graph is coordinatized. I should mention, by the way, that the thing I'm currently working on is trying to get effectively a phase tester working so that we don't have to explicitly coordinatize. So it will just look at branch pair ancestry and infer the phase from that.
Okay, that's an interesting idea.
That will allow us to do a more realistic kind of cancellation thing. But for the time,
hold on. So you're saying, given a branch history, okay, that should give you relative phase information.
Right, because we can look at 1, 0, and 0, 1 in this particular case, and we can work out that because their common ancestor is very far back, that they're going to cancel out pretty conclusively.
Wait a second. So let's imagine that we know given that it's a tree, and we know how far back in the ancestry it is, we know that in d dimensions, that means if every branch, if it's exponential dimensional, every branch is orthogonal in a new dimension.
Right.
So if you go back, k steps, you have k orthogonal moves in d-dimensional space. You're going. It's essentially like a quotes random walk. So you take k steps, each in a different dimension. Gosh, how to think about that? I mean, that's life in Hilbert space, because that's making you. Okay, hold on. So at every step, you are orthogonal to this. You go out in another dimension, and you're going along the coordinate axes. So essentially, what you're doing, I see. So you've got an n-dimensional hypercube, k-dimensional hypercube, and what you're doing is you're simply going down. Yeah, actually, that's easier to understand.
Yeah.
At every step, you go. The two members of the branch pair go on opposite. They have reached a particular corner in the hypercube. Okay?
Right. And then you go back and you find the last common corner, and that tells you the projection.
Okay, we're going to do this. When you finish this demo, I have an interesting idea here about what to do with this hypercube.
I've partially completed code for that, but it's not quite done. That's my next thing.
Okay, but I have an idea. Okay, and you want to go on? Is there more to see here, and then we can?
Yeah, of course. So the reason I wanted to show was to explain what I think we should investigate here. So let me do a more complicated, more interesting multi-way system. So let's do a. Let me think of an example.
There was a previous. Ethan was asking about Toffoli gates.
Yeah, we could do a Toffoli gate, but the problem with the Toffoli gate is that it's basically classical. So for those of you who don't know, a Toffoli gate is effectively like a kind of C0 gate, but where the 1-0 swap is in a slightly different place. But we did a bunch of stuff. I sent Stephen. I think I sent you a notebook with some Toffoli gates and Fredkin gates and things set up there, but that didn't end up being super interesting. So I'm going to do a Fourier transform because I think that's going to be more
exciting.
Talking
of which, I have still not heard from Ed Fredkin, which is really quite alarming. I also heard, I gather, we still haven't heard back from Roger Penrose, and I heard that he had some slight health issue. So hopefully we will find out more soon.
Okay, it's a slightly more complicated looking multi-way system. So let's now do something like that, evolution graph. So okay, and so just
what is this? What are we looking at here? Okay, so that's
I'm doing a Fourier transform. So that's, well, if I do, I'm out by a factor of 2. That's our discrete Fourier transform, or
a very boring Fourier transform. Could you show me a Fourier transform of some more interesting vector?
Give me an interesting vector. I don't know, 0, 1, -1, 2, whatever. Oh, hang on, sorry.
The
What
I
am I
is
doing?
not going to make it. No, you can't.
No.
You
That's
have to
not
have
the issue.
some
That's not the
combination of
issue.
basis elements.
Yeah, sorry, I completely forgot what my framework does for a moment. I can do.
Yeah. By the way, you should probably have a function that does this thing about
Yes. Absolutely.
Doing rational approximations basically to things. All right.
That's a more interesting vector.
Okay. So now combine those in the results. Do the combination of those results, and let's see whether it agrees with. And so what you're saying there is in that output. Well, go ahead.
Okay, so right, so that's actually a little bit non-trivial, but let's try to do that. So because we have to, we can, as well as getting the states, we also actually have to get the
path weights.
We have to get the path weights, and there's not a really straightforward way of doing that, but we can try. So let's do a property value graph. Yeah, sorry, I'm getting ahead of myself. Let's do a property value graph vertex weight. Vertex weights? No, wait. How does this work? There we go. Okay, and then if we do vertex list of graph, and then we do a, let's do last / at that, and then do a thread. Does this make sense? Yes, okay. Right.
By the way, I just want to comment on Richard on the live stream saying that he hopes Roger Penrose is okay. So do I. I think I'm going to find out more from a mutual friend of ours later today. So, I think to make the comment, I think the more that we explore this whole project, the more Roger, I think, is probably the most prescient person in terms of having seen a bunch of the directions that we're going in, although the details of what he's actually studied are a little different. But so yes, we're keen to chat with him.
Okay, so that's
hopefully soon. Okay.
So then if we do select of these first hash, wait. Does that make sense? No, wait, other way around. There we go. Okay, right. So that should be all of the things with their respective path weights.
Yep. Now you just have to combine them according to the path weights.
So now if we say, if we do
just multiply the things. Just
yeah.
First of that times last of that, and then total.
Oh, let me sorry. Since I bothered to do that, let's do.
I'm very suspicious about that 2 times that thing. Not
of course.
There's strings.
Yeah.
Strings.
So it's fine. We can do that maybe.
Yeah, I would do that.
Oh, hang on.
It's not a string or a box. No, it's because you want 2 expression of first. You've got first of 2 expression. You want
oh gosh, yeah. So I do. Quench. Hey, okay. Right. Okay, that looks possible.
Okay.
So now
back at the
Fourier. Yeah, what did we do? It was 1 plus I, and 1 minus 1. Oop. 1 minus 1. Oh no, hang on, wait, sorry. I did a 1 and then a minus 1 for no reason. So it's actually a 0, and then I picked a very bad vector. 0, 0, 1. So if we multiply that by 3. No, wait, hang on. Was that right?
Okay, let's take the vector you had there. Take your initial vector. Take your initial vector. Back up. Okay. Take that thing there. The operator. Oh, you've got the operator there. So the initial vector. Just copy your whole initial vector.
That's a bad thing. Hang on. Let me remove that. That will hopefully make it a bit clearer.
Did you do the total?
Yes. Hang on. Let me figure out what's gone wrong.
No, I don't think you did total there. Just rerun it. You didn't do the total. It didn't.
Didn't I?
No.
That total?
Yeah, do that total. That total.
Yeah.
Just run it.
Yeah.
Okay, you did do it. Okay. Now try running. Now look back at your original input. Okay, now just copy out that input, the 100. Just copy that thing out,
Mhm.
and now say total of that.
Well, okay.
And that will give you your initial vector.
Mm-hmm. Right. 1 plus
So
I
now,
0, 0, 1. Yep.
okay. And now.
So the thing that's making me wonder about this is. Did I input this matrix incorrectly? Hang on. That's probably the most likely thing. So that's minus I minus 1I, 1 minus 1, 1 minus 1, 1I minus 1 minus I.
What should it be? It should be some circulant matrix or something? What is that?
Yeah, but hang on, wait. So let's actually check that the arithmetic is right. It could just be a bug in my function. That's probably the most likely thing. So
2 plus I, is that the Fourier transform? It's not the Fourier transform.
That is not the Fourier transform. So the matrix.
All right, so something has gone wrong.
So the matrix is wrong. It's okay, which means which fortunately means it's probably not an issue with my function. So
all right, but what I want to see, did you manage to get any of the? Okay, so what we've got here, first thing is we need to understand better the interpretation in branch shield space. But I think what we've got here is a thing which will make a multi-way system out of a integer quantum operator, basically.
Right. Anyway, so the point I was making was if we take this thing.
And what's the I? I mean, how do we think about the I in the quantum operator?
That's another mutual direction. You know, that's just another 90-degree direction.
Okay. Yep.
So it's just another. Yeah, it's another thing we have to coordinatize for convenience purposes. But if we do something like that, okay. So even though this isn't quite a Fourier transform, it's a reasonable enough approximation. We get a complicated multi-way system. But here's what I want to figure out. So within our formalism, I think the prediction is that the reason why quantum computers are ostensibly faster than classical ones is because if we look at the so if this is our graph, what we're effectively doing here is 3 quantum operations, which would require on the order of 100 classical operations. If you were to, if you think of each operation on an individual eigenstate as being a classical operation. But what I would like to try and figure out is if we now take, well, hang on, we could just do the simple case of this. If we do something like that, so we say Knuth-Bendix completion. So we can ask what's the minimal set of states that would be required to force this evolution to be causal invariant from here on out, or evolution causal invariant. We get some complicated looking thing. And then what we could, so that's our completion rules. And then we can say, if we take quantum to multi-way system, and actually this is going to be useful. So if I want to take the final state here, so that's going to be
with the path weights.
Yeah, actually let's do it without, just because it's going to be easier. But
okay.
So let's do select.
I understand what you're going to try to do. You're going to trying to say the measurement operations correspond to the Knuth-Bendix completion operations, and then you want to count the number of measurement operations that are needed to make a single conclusion from this.
Exactly. So what I want to work out, actually, sorry, we don't actually want this quantum multi-way system. We just want a regular multi-way system. This is our initial.
And you want
state.
to know how many Knuth-Bendix completions. You want to rerun the thing after you've done that number of states. Then you want to run it with the Knuth-Bendix completions and see what it takes to resolve it.
Right. Exactly. So if we now take this thing and we deleted too much. So if we get this is our set of rules. That's the set of completion rules. So if we now do a join of rules with completion rules, and I think it should delete duplicates, but just in case it doesn't, let's delete duplicates. And then I think that's everything that we need. So that should be this thing here, which is an incredibly complicated. And so actually we can just check
Is it a one-step completion? Do the Knuth-Bendix completions do it in one step?
Yeah. So if, or this particular kind, sorry. 2 steps. There we go. Okay, evolution causal invariant. So that's what we wanted. So now if we do evolution graph, and then we say edge list of that. Oh, sorry, we want to do length of edge list. 184. So actually,
okay,
let's
unroll what you just did, because it's actually pretty interesting. Okay. Mm-hmm. So the claim is, it's actually very interesting. Okay. The claim is that you do the quantum evolution. It takes, you are doing in 3 steps, 3 quantum steps, what takes 116 classical steps to do.
Right. You've saved 113 steps by using your quantum computer.
Right. Okay. Now you say, but I want to resolve it to get to a classical answer.
Right.
And we're saying we have a way to do that by adding in Knuth-Bendix completions that serve the purpose of causing that superposition of quantum states to be degenerated basically down to a single classical state.
Exactly.
Okay. But we have, how many Knuth-Bendix completions does it take to do that? I mean, in completion rules, what's length of completion rules?
122.
Okay.
Pretty bad.
But those completion rules, let's be clear on what was done here. Those completion rules, in maybe kind of complicated, but in one step, they managed to successfully measure the thing and reduce it to a classical state.
Exactly.
Right? So that might not be the way you'd actually do it in practice. But this is a toy version of how you do the measurement.
Yes, and so it's important to say there's a trade-off that we have to consider here, right? Because in building an actual quantum computer, you probably don't want to reduce it to an exactly classical state. You just want it to be right, within some margin of error. And so what we want to work out is what exactly is that trade-off. So if we have less good completion rules that maybe take longer to resolve it to a causal invariant thing, or it doesn't resolve to a causal invariant thing, but it resolves to something approximately causal invariant. What's the length of the, what's the computational complexity associated with that? But the thing that I think is interesting and that you can immediately see with this function is that if you want to do a true completion procedure, in all but the most trivial cases, any advantage you get from running this thing in parallel effectively is at least partially cancelled out by the complexity of the measurement.
Right, but so let's just understand how what the asymptotics of that actually is. Okay. So in rough approximation, let's take. Can we take? Yeah.
By the way, I that was all I wanted to start it off by showing this, but I'm happy for you to take control again.
Why don't you save this notebook out, and so long as I can run it, we can.
Sure. I'll send it to you now.
Okay. Okay. All right, we got several things that I wanted to make sure we do here. Oh gosh. Actually, you know what? I am going to restart my desktop because I was doing some giant things in here before, and I'm a little worried that I've got hundreds of gigabytes of state that I don't really need. First, I have to have this actually launched. There we go. Okay. Let's expand it so people can see it. And do we have a section here about quantum computing already? Quantum compilation. Okay, let's start off quantum computing. Well, actually, let me just make this quantum 11 because I don't really know what we had there. Okay. I'll pull up your notebook in a second. Well, actually, let me pull it up right now. Oh gosh, what is all of this? This is the quantum to multiway Oh, these are functions that I have to run. So are those in the appropriate places? Do I need to? Should I get these versions? Should I be running these versions, Jonathan?
Yes, yeah, you should. I haven't put them in Dropbox yet because I was working on them right before the stream.
Okay. Okay, here we go. So what I would like to see from here is what is the the sort of quantum gate quantum versus quantum operation counts. And I want to compare what how does the operation count increase with the size of the system and so on. So in other words, in the classical case, what do we expect? In the quantum case, what do we expect? So can we take the example of Fourier transform?
Yes,
where this is
whatever approximation to the Fourier transform we have. Yeah.
Well, but can't we just count the number of in your setup here?
Mm-hmm.
We can surely count. I mean, it depends on the precision. So there are several pieces of input. The e.g. Fourier transform, quantum Fourier transform. And what's sort of interesting is that there are two things that affect the number of operations. The operation count is affected by the size of the transform and the precision of the transform, is it not? Because the way you're doing it is which is kind of interesting and perhaps somewhat realistic. Okay,
right,
so
because the path weights also matter.
Right. Okay, so then let's just count for a transform of size n. How many operations are there? Isn't it the case that for a transform of size n, a precision, p, let's say.
Mm-hmm. It's probably. I mean, it looks like 4np.
But you only have to do one step here to get the transform.
Yeah, I mean it's one operator.
Okay. So where p is the maximum size of number that you need to get the precision.
Mm-hmm.
Okay, but then okay, the size n of the transform and the precision p measured by the denominator, basically. That's the maximum denominator, I think.
Uh-huh.
Okay, so the claim is that in that case, what you need is, I don't understand why it's 4. Why it isn't n squared? How big is this? Isn't this an n squared matrix? And doesn't it have an edge for every element?
Oh, sorry, that's what you meant by length. I assumed you meant length in terms of number of basis elements.
No, the basis elements are 2 to the n. Are they? Or no, the basis elements are just n.
Yeah, and I was saying 4 because for each basis element there are 4 evolution edges.
Okay, but what I'm trying to do, I'm trying to understand what is the classical count.
In that case, if you're talking about numbers of subsystems and it's a qubits rather than a qubit thing, then it's 2 to the n times p times whatever the intrinsic complexity of the Fourier transform is, which looks like 4 in this case.
Okay, so let's just write down what that is. So the operation count, the analogous classical operation count is 2 to the n times 4 times this p quantity.
I think so, yeah.
Okay, so then that is the classical version, classical operations, whereas the quantum operation in that case is just 1, right? There's just one quantum operation here.
Uh-huh.
Correct? Okay,
right.
So now, compared to that, let's look at the number of completions that we need.
Well, I suppose, hang on, wait, do I believe this? You could argue it's actually p. Maybe, I don't know.
Either 1 or p, I understand the issue. I mean, because we've got these different subsystems.
Right, right.
And it's 1 or p. Okay. Okay. So now the question is, how many completions do you need to resolve this? Right? And how does that scale with n? Because that's the critical thing. Does that scale with n? You know, because here we've got quantum operations is just 1, but we have more. But these completion operations, you know, really isn't the thing we want to look at the number of completion rules, not the actual operation count here, because that operation count is again somehow a classical operation count.
Yes, maybe. The reason I think it's useful to think of the operation. So the problem is that the length of the number of rules seems to me to be an algorithmic complexity measure as opposed to a computational complexity measure.
Yeah, but it'd be interesting to know how they scale, because
absolutely.
The fact is that what's happening here is, okay, let's look at the bigger picture. The physics of what's going on is you have, you know, the quantum algorithm is exploring all these different parts of quantum space in all these different little corners. But for you, when you measure it, you have to corral all those corners together to get to your to route the sort of quantum information to that part of branch shield space where your measurement is being done, in some sense.
Right.
And the question is, how do you do now? In the quotes real case, you would have built your quantum computer to use the exact same physics as the evolution thing. But here we're kind of faking that by saying we're going to invent new rules. Let's just think about the following contrast again. So we've discussed 2 ways that you can do an experiment. In fact, this is the thing we really need to 2 approaches to experiments. Approach 1 is you explicitly conceptually set up a state. And 2, you wait for the universe to deliver the state you want to study.
Right. This is the generational versus ordinary multi-way system distinction.
I need to understand that better. So let me understand that. I mean, so this second one is the much more realistic one, because that's the no free will version, right?
Right.
The other one is you imagine you have free will. Imagine the experimenter has free will, as opposed to living in a deterministic universe.
Right.
Okay, so what's your statement about generational multi-way systems, and how does that relate to this?
So you remember when, obviously the generational multi-way system evolves by just applying maximally consistent space-like separated collections of events.
Yep.
And so they are effectively the purely classical states that you can see. And any branches that appear must therefore be pure branch-like separations. So if you want to measure a classical state, you can either wait for the universe, because every state in the generational multi-way system will eventually correspond to a state in the ordinary multi-way system.
I see what you're saying.
You can either wait for it to appear, or you construct your quantum observation frame so that it assembles a collection of space-like separated states, and you assemble the generational multi-way state.
Okay, that's a good way to think about it. Okay, so what you're saying is, in this case, you wait for the thing. So this case here is like analogous to generational multi-way system, where you insist on having done all the updates necessary to reach a classical state.
Right.
And this case is you wait for the universe, you wait for causal invariance to deliver you the classical state. Okay, and it is our experience of the world, and we need to understand this better. But it is basically our experience of the world that it seems classical because, in fact, we succeed in waiting long enough for causal invariance to do this. I mean, you have a slightly different interpretation of this.
Right. But I think they're basically, philosophically, they're kind of the same, right? So when you, in the pictures in your tech paper, when you're walling off those classical states with quantum observation frames, those classical states that you wall off are exactly the ones that would appear in the generational multi-way system.
Yes, fair enough. Okay, but anyway, so here, okay, the thing I'm trying to understand. So I mean, the big picture here is, because we have a way, so our representation of measurement, we're doing an experiment one of these two ways. Either you're simply waiting for the universe to deliver through causal invariance to deliver you down to the state you want, or you are explicitly putting in completions. Now, I suspect that there is a difference between those two things. That is, it's just like in theorem proving, right? When you put in completions, you're speeding up the theorem proving.
Exactly.
By what factor?
So it's usually, so in the most general case, it's exponential. It's usually sub-exponential.
Yeah. Right. So by inserting completions, you are going to basically to case one.
Right. Theorem proving in arbitrary equational systems is exponential complexity, whereas theorem proving in confluent systems is polynomial complexity in the worst case.
Okay, so this is so it's analogous to completions in theorem proving. Somebody is asking, can we make this even bigger? Okay. When we start doing more computations, it's going to make it hard to make them this big, but okay. So the question is, okay, so this is analogous to adding completions in theorem proving, which in general, and completions in theorem proving, which is analogous to adding lemmas, i.e. adding lemmas in theorem proving. And we know that that adding lemmas is an exponential speedup.
Right.
So what's interesting here is that the just wait for the thing to happen is exponentially slow compared to force the measurement, so to speak, by completions. It's kind of interesting.
Mm-hmm.
But even the completions appear to be very, very slow. Even if you are delivering the completions on a platter, it still seems to be very slow to do the measurement.
Right. And of course, the completions themselves have unbounded complexity.
You mean the number of completions you might need to be able to make it confluent?
Yeah. The worst time, the worst case time complexity is infinite.
Sure. Yeah, it's not looking good for. I mean, so let's talk about this as a practical matter for a quantum computer, right? So how do you see this effect? You see this effect because basically you have just done your giant factoring problem, and you are trying to actually measure it, trying to actually get a measurement of the result. And the question is, I mean, I don't know, in these different technologies, there are different ways to do that. And it might be interesting to kind of trace it through and see what's actually involved in doing it. Do you know enough to know that?
No, not on the experimental side, no.
We should get somebody from one of the companies or whatever and just ask them.
Right.
Okay. So, all right. So I want to come back then to visualizing branch hill space. Okay. So what we've discussed is, I mean, in a sense, what we're doing is we're saying it's a grid graph. The branch hill space is a grid graph. Let's say it's a 4-dimensional grid graph like this. Well, 3-dimensional case would be like this. So we're saying, every branch, the things go in two orthogonal directions, right? So let's just show that here because we can kind of illustrate that. Oh, great. Well, okay, so let's just pick here, highlight graph. I don't even know how to do this. How do I do this? I want to pick just 2 outgoing edges from one of these nodes. Well, here, let me do this. Let's do it in the simple-minded way. Okay, so we're going to pick from 1, we're going to go to 3 and 5. Okay, so we say highlight graph. So my claim is, what do I want to do? I want to go from, I want the subgraph of that. The 1, 3, 5 subgraph, I think. Yeah, okay, there we go. Okay, so that's our first branch pair. Does that make sense?
Yep.
Okay, the second branch pair will live in a higher dimensional space. So the second branch pair in this setup would be in, so here, okay, so that's our first branch pair there. So our second branch pair from any one of those outputs would now be orthogonal again. Right? It would go to this edge and this edge, for example. Make sense?
Mm-hmm.
Now, an interesting visualization idea might be if we take the grid graph. Yeah, this is actually not a totally stupid idea. Okay, so let's take this, and let's say 7-dimensional. Okay, so that is a representation of a 7-dimensional hypersphere. And how is it embedding its points? Any idea? Let's look at this. Let's look at the question of, so the metric here between 2 neighboring points.
Whatever the embedding is, it's very similar to the embedding people use for Dinkin diagrams of large Lie algebras.
Yes, it is. I don't know what that embedding is either, but I mean, let's see if it helps us to go to 3D. Not really.
Try 3D printing that.
Yeah, it'll be cool. Not really, but the point is that what we're trying to represent here is orthogonality in, 7 levels of orthogonality, right? And so my claim is that if we're trying to visualize branch Hill space, that, you know what, I had a picture like this in my tech paper here. I think I might have already been ahead of this. Hold on 1 second, let me pull it up. Let's see. I think I had a discussion about branch Hill space. Foliations in the structure of branch Hill space. Not there. Typical forms of branch Hill graphs. Lovely. Oh, there we go. There it is. Ah, Richard on our live stream is saying it's called a Petri projection. Okay. Which we should look up because I don't know exactly what that is. I remember there's a chap called Petri. He was a Cambridge mathematician, if I remember correctly. Maybe I'm wrong. Let's look it up. Oh, interesting. Okay. Huh. Okay. Regular polygon. Is this the same thing? Regular polychora, 4 polytopes. This seems relevant.
Yeah, I'm looking at it now. Oh, he was a lifelong friend of Coxeter, who named the polytopes after him.
Uh-huh.
Interesting.
I've definitely heard of this guy. Okay, so but in any case, this is an embedding. It's not completely clear on why Petri polygon of the tesseract is an octagon. Each triple of consecutive sides belongs to one of 8 cubic cells. This is EdPeg territory.
Oh yeah, and it is the Petri projection that's used in representing exceptional Lie algebras and things, and the exceptional Lie groups.
Right. Calais on our live stream is pointing out that Jim Gates was also talking about mapping particle exchanges onto edges of a hypercube. Right. And okay, so but in any case, what we want to do here is we're trying to get a visualization of branch Hill space. And what we're saying is that on every branch pair, we are making another orthogonal choice, right? But one thing that's bothering me, I guess we don't know which orthogonal choice we're making. Ah, I see. That we do in fact know, because there is merging in this thing, that will determine. I mean, that is, this is sort of the substrate on which we're doing things, but the actual choice of which once we're at one of these points, right, we can always go, I'm getting confused here. Each branch pair effectively adds a new dimension. So in some sense, if we're going to go D branch pairs down, we are making various choices, right? So in other words, we're trying to render one of our trees onto one of these tesseract projections.
Mm-hmm.
But where we actually put the tree on the tesseract, or whatever it is, on this Petri projection thingy, what determines that? I think it's determined by, because in the case of the hypergraph, what determines it is when two JD6 land on the same element. See what I'm saying? So here, I think we have the same issue, that we thought we were making separate branch pairs, but actually some things landed on the same element.
Mm-hmm.
But what that's saying is that is what structures our space, so to speak. Without that, we just have a tree. Right? Without that, we have a tree that doesn't fold back on itself, and we don't know anything about the structure of that space. It's just exponentially growing, and nothing folds back. And that would be the kind of the trivial outer product Hilbert space would be just the pure tree.
Mm-hmm. Right. You need to have information about mergings in order for things not to just all be perpendicular.
Yes. But I mean, it's not good enough. No, they can be perpendicular. That's fine. It's useful to represent them as perpendicular here. I think that's okay. The difficulty is, and now I'm going to ask some questions about projective space here, because I think that might be relevant. But okay, it's okay to represent them as perpendicular, but you have too many degrees of freedom if they're just saying they're perpendicular, right? But
right.
In other words, you've got this big floppy thing, and it's perpendicular at every step, but you have constraints that allow you. So really what we have is the analog of a graph embedding problem, but we are looking at, so what is the analog? In graph embedding, what we're trying to do, we've got the spring electrical approach to doing graph embedding. What is the analogous thing here? In other words, we're trying to approximately solve a bunch of constraint equations that describe this multiway graph, which we are now laying out on this high-dimensional hypercube, so to speak. Right. So the question is, given a graph, we want to lay out the graph on a high-dimensional hypercube. how does that relate to laying out a graph on hyperbolic space? Is it related or is it not related? How does this Petri projection, for example, relate to, I mean, in hyperbolic space?
Are you going to mention Poincare disks?
Well, I am, yes, but I mean, but we can't do, can we, what happens to the n hypercube on a Poincare disk? Is it interesting or is that not, it's not the same thing. It's not,
why, I'm confused. Why are we talking about hyperbolic geometry? We don't know the geometry of these things.
No, I know we don't. We're trying to get okay. So what we're saying is, in a first approximation,
assume it's flat?
We can assume it's flat. I'm trying to get a sense. Okay, I'm trying to understand what is the constraint problem. Okay, so we've got an n-level multiway graph. Okay,
right.
So I'm saying we're laying out the n-level multiway graph on an n hypercube.
Yep.
Okay, but the question is, how does the graph lay out on the hypercube?
Mm-hmm. Right, I understand. But the hypercube isn't hyperbolic.
Well, I understand that's what you're saying. I'm trying to understand how do we. So this is a reasonable projection of the hypercube. So my question would be, okay. So here's the question. Let's take a multiway graph, some random friendly multiway graph. Okay, I think I understand how to formulate the question. Okay, so we've got a multiway graph. Give me a multiway graph that is some reasonably merging multiway graph. Let's pick one of these guys here. How about this one here? Okay. All right. So now the question is, if I want to lay this out on a one, okay, so that's a 2 cube, right? I'd lay that thing out in a square, right? Now I'm going to lay this out in a cube and this out in a tesseract, right?
Yeah, I understand.
And so the question is, how do we?
What's the constraint problem? I think we agree.
The constraint problem is those have to wind up on. I mean, these could end up, if I'm not mistaken, they could end up distant in the hypercube and not able to reconverge like this. Is that true, or am I confused? Can you always lay this out on a? So every one of these is an orthogonal branch.
Mm-hmm.
How do we do this? Hey, Max, do you have an idea?
Well, not immediately.
Okay.
Right, but we all agree on the problem. I think that we want the answers, the natural.
Right. But so hold on. So we're trying to put this. Maybe we can do this by hand for this case. Right. So let's do it for the cube here. Okay. So what we're going to do is we're going to take the cube, otherwise known as grid graph 222. Okay. So our goal is to take that grid graph and basically be able to put, so AA becomes one of the, let's put the vertex labels in here. Okay, so the claim would be like 1 goes to AA. Given that 1 went to AA, let's say we say 2 goes to AAB. Oops. Three goes to ABA. Fine. Now, where do we go next? So in fact, let me actually put that in there. Vertex labels, well, actually, I can't do that. So I would be, let's do this again and say, okay, this is what I get for having such a big, I've got to make this slightly smaller. Sorry, guys. Okay, so we got AA, AAB. Okay, so where do we go next? Now we've got AABB. We got AAB and ABA. AAB and ABA have to merge on ABAB, so that forces ABAB to be number 4. Correct? AB can't be,
Yeah.
for example, here because they wouldn't merge. Okay, so the next thing we can do is ABBA is orthogonal to ABA, so that it's one of the ones, but it can't be there, so it has to be down there, so it has to be 7. Right, that it has no choice.
So ABAB should have 4 neighbors, but there are only 3 edges coming out of it.
No, but that's because we need to go to the next level of tesseract. We need to go, in order to represent this whole thing, we got to go to a tesseract. We only can get 3 levels in a 3 cube.
Right, makes sense.
So AB, what was the other one that I had? So then we got ABA goes to ABBA, and we got one last one to do, which is AABB, which is AAB goes to, okay, so that has to be down there. That has to be 6. AABB. Okay, so I claim that's uniquely determined now by this set of connections uniquely determines how we lay it out on that function. Let's see. We have various comments on our live stream. Maybe somebody can solve this there. Okay, Ethan is asking for neural net stuff in 12.2. That is not. Don't worry, we are working on it. In fact, my meeting 2 before this one was about that, and we will live stream some more neural net discussions. That was a rather detailed, more about strategy of who does what than about what we're doing. Okay, so maybe you can visualize your D6 in Hilbert space by projecting onto 2 dimensions, where each dimension is represented by a different fixed angle on the plane. Not completely understanding, but it's an interesting potential idea. Yeah, we didn't know what we were. Let's see. Okay, so look, let's just let's think about this algorithm problem a little bit, and if we maybe can, who would be the most helpful person to understand how to do this algorithm? Boy. Okay, so but the basic point is we are thinking of the analog of doing graph layout in branch hill space is layout on a hypercube. How do you lay out a graph on a hypercube? There's got to be a way to think about that.
Yeah. It's the embedding problem for cubical graphs.
What do you mean?
What do you mean? If you have a cubical
hypercube
graph,
is not a cubical graph. A hypercube in general, an n hypercube is an n-ary rather than cubical. It's not a trivalent graph. I didn't understand that idea. I mean, what you've got to do is, look, what you're trying to do is you're trying to drape a graph over this hypercube.
Yeah.
And then the question is going to be,
so surely you just have some graph that has 2 to the n vertices, 2 to the n-1 times n edges. So it's some direct generalization of a cubical graph, which is regular or close to regular.
Yeah, but it's not a layout of that graph. It's a layout on that graph.
Yeah,
not quite the same thing. So I mean, it's asking the question, and then the end result that you want to get is, for our visualization purposes, we're saying things are at the opposite end of branch hill space if they are, for example, at opposite corners of the hypercube, I believe. Right? That means if they were at opposite corners of the hypercube, I think that means that they took all of the, all the opposite turns in some sense in their branchings. If each branching is orthogonal to the, if the two branches that come out are always orthogonal, look, I mean, the basic point here is we're trying to get some visualization. So far, actually, wait a minute. So what will be the analog? So right now, when we lay out branch hill space, so for example, here, we could take this thing and we could lay out the branch hill graph. Boring. Very boring. Why is this such a boring one? Oh, it's just going to be a grid of some kind. Well, whatever. Let me add something else in here. Let's say B goes to A. Okay, that's a more interesting branch hill graph. So that's showing one-step ancestry. Right, that's a way of saying what's close to what. This is trying to show for all step ancestry. This is, in other words, this is giving us some layout information about branch hill space, but it's only based on one level, one step branching, so to speak. Right, we could imagine a similar picture. See, this is, the problem is if it branched 3 steps ago, then it's already very, very far away because it branched out and it's orthogonal from 3 steps back. That makes sense?
Yeah.
What's that?
Didn't we already agree on this? That we're doing an embedding problem. We want it to match. We want the natural embedding metric to match the. We want the embedding metric to match the natural ancestry metric on the multiway system. Right.
Indeed, but how do we do it?
Well, yeah, I mean, I don't know. I'm not. I don't. Graph, graph visualization is not my thing. But I'm just. Isn't that the problem? Didn't we already agree?
Yes, we that's the problem. We're trying to solve the problem. Okay, I'm just trying to formulate the problem in a way that we can imagine solving it. So this is using regular graph embedding, using so in a sense, what we want is we want the ancestry distance. Yeah, here's one way to think about it. Take the ancestry distance, and the further back they branch, the further apart they should be.
Well, unless they need to merge soon in the future.
But you can't know that in any finite amount of time. Right, we only want to construct an embedding that's asymptotically correct.
Let's take, okay, so, we've got your, wherever it was, your quantum computing thing, and we're saying you have got this thing here, and you're trying to understand these -1 things. Are they going to wind up on the opposite side of branch hill space here? Because we could just think about this representation. Would they end up at the antipodal points here?
Right, if this is embedded in such a way that it preserves the ancestry distance, then yes.
Okay, but so let's take this picture and label it by quantum phase. See what I'm saying? So in other words, we're imagining this is a representation of our GD6, and we can say effectively what the phase of each GD6 is. Is it sufficient? Can we think about it in terms of I mean, what is the phase difference between that GD6 and this GD6? Can we figure that out?
Sure, we can compute their ancestry distance.
And what do you think the relationship is between, okay, so let's say ancestry distance.
Well, the ancestry distance tells you the value of the projection. And once you have the value of the projection, that's trivially inconvertible with the angle.
Okay, so let's say it's ancestry distance k between nodes. Okay, so given that, what is the phase difference between those nodes? So let's say they have ancestry distance k. What is their phase difference? I think there's a coefficient, there's a factor, which is probably related to h bar. But go ahead.
So obviously the value of the projection is then just k over, 1 minus k over L, where L is the number of layers of the multiway system.
I don't understand that. So hold on.
Right.
Look, what we're claiming is that at every step. Go ahead.
Yeah, if you have to go back to the root node, that's an ancestry distance of L, which corresponds to a projection of 0. If they have 0 ancestry distance, that corresponds to 1 minus 0, so they have a projection of 1. Anywhere in between, their projection is somewhere in between. Once you have the projection, that's trivially interconvertible with the angle.
Sure is.
So it's 1 minus k over L.
Why? Why is it linear like that? Right, 1 minus k. K is typically a big number, like 18 or something.
Yeah.
But why is it a negative number? I don't understand. I mean, you're saying
1 minus 18 over 20 is not a negative number.
1 minus 18. Oh, 1 minus 18 over 20.
K over L is the fraction of the ancestry distance, is the ratio of the ancestry distance to the number of layers of the multiway system, which is the fraction. If you project one geodesic onto another, it's the fraction of the first geodesic
I was misparsing what you were saying.
Minus
yes,
K over L.
Right. So you're saying it's 1 minus, but in a sense that there is a coefficient in front of that, which is some kind of h barish coefficient, because that's telling you.
No, in natural units of when you're just talking about the projection, it's just that. If you then want to assign some kind of physical quantity to it, I agree. There's an h bar factor.
Right. Well, okay. So humph. All right. All right. What else should we try to figure out here? So the goal was to take. We've got some level of quantum compilation happening here. We think we understand more or less how that works. We don't yet fully understand how this cancellation stuff works, although it's fairly clear how it works, but we don't have great visualizations of it working. I mean, we'd like to. Go ahead.
Yeah, I'm almost to the point where I have code that actually computes these cancellations, but obviously it doesn't visualize them. This is just combinatorics.
Yes, but conceptually, the reason the cancellation is happening is because the things have wound up on opposite sides of branch Hill space. And the claim is that when we want to take a limit, what exactly is the claim? So we've ended up with these two GD6 have ended up at different sides of branch Hill space. And yeah, I mean, basically, the intuition is as soon as you try to measure them by sampling some part of branch Hill space, you will never get them both. So, they can never, they never contribute sort of in the same direction, so to speak.
Right.
Yeah, I think, I mean, okay, so let's review what we need to do. So we've got, visualization of branch Hill space. What can we do there? And I mean, maybe these visualizations are I don't know. I mean, it's tricky because this really isn't with the spatial hypergraph, we are lucky in the sense that the visualization of that corresponds to our everyday experience of ordinary space because it's supposed to represent that. We don't have intuition about the everyday, we don't have an everyday representation of the space of quantum states. So we don't get to have that, we don't get to leverage our experience with visualizing the space of quantum states because we have no experience of that, basically. I really have not seen, I've just in the various quantum, I'm probably out of date in my quantum books, but I don't remember anything having any reasonable visualization of that. Do you agree with that statement? I just I can't think of anybody who has, it just seems like I'm just picking up here. I happen to have a book by a employee of ours, actually, Cy Blinder, about quantum mechanics, which I think has various visualizations in it. And I was just looking through it here to see whether there's anything. I think it looks like he has fairly traditional visualizations, which don't. He's got some nice Wolfram language. Oh, look, he's got some nice stuff here. Well, you see, he sent this to me, but I wasn't thinking about physics at the time when it arrived. Okay. All right. In any case,
I had a discrete analysis professor once who was trying to explain how to visualize sort of 38-dimensional Banach spaces. And his explanation was to visualize 3-dimensional space and then say 38 very loudly to yourself.
That sounds slightly unconvincing to me.
Right.
All right. Okay. Let's Richard on our live stream is mentioning various things about embedding hypercube graphs on orientable surfaces and Eulerian circuit embedding. Yes, you can certainly wind the thing round. Any graph embeds in 3 dimensions, so it's but I don't think it helps one in having a faithful embedding in the sense that sort of distances in branchial space correspond to things that, there's absolutely no reason why distances in physical space, why we should be able to do this visualization, and perhaps we just can't. We might be lucky that in some simple cases we could see what was going on. But I'm feeling, yeah. So okay, so the rest of this roadmap involves, we can understand how to do measurement in terms of completions. It will be really good to understand how to map that onto the sort of physical instances of measurement in quantum computers. That would be an interesting thing to work out. Maybe that's a summer school project to try to actually map it into physical into the various technologies of physical quantum computers. All right, you want to try? Should we try one different topic for a minute if we think we've sort of mined this particular topic?
I think it'd be nice to do some systematic explorations of measurement procedures, but we could do that another time.
What are you suggesting there? You're saying given a particular.
So looking at exactly the analysis I did earlier, but with a kind of larger class of, I guess there are 2 things. There's the thing you suggested earlier, which was taking random multi-way systems and seeing what they look like when represented as quantum gates.
All right, let's do that.
But similarly, I think possibly a more interesting thing is then to figure out what's the trade-off in the complexity of the evolution versus measurement operations.
Right.
For generic multi-way systems.
Right. Okay. Let's do the enumeration of. There's a question from William about branch triplets or branch n-tuples. Actually, Seth Chandler wrote a nice piece about the generalization of branch pairs. For this purpose, the branch pairs do not have to do with qubits. They don't have to do with the binariness of qubits. They have to do with, what's the right way to think about this? They have to do with given a state, you can
They have
always go ahead.
They have to do with the binariness of the projection operator.
What do you mean?
That a dot product is a binary operation.
Well, the way they're generated in a multi-way system is we're just asking, like in this multi-way system, wait a minute, in general, we can have many, I mean, the fact that this is a binary case is just
Yeah.
happens
Obviously,
to be that way.
anytime you have a tuple, you can represent it as two branch pairs and so on. Right. The reason we represent them as branch pairs as opposed to branch arbitrary, sorry, not a tuple. If you had a triple, you could represent it as two branch pairs. If you had,
Yeah. How do we see that example? We can get that example by saying something like this, can we not? Yeah. So we'll have plenty of things here which are not. Now I'm confusing myself.
Right. So each pair of those of those three is an independent branch.
Oh,
pair.
that's right. That's right. Because what we care about is a single dot product of those two things.
Exactly. So to induce a geometry, you only need to consider pairs of them because the projection operation is a binary operator.
Yes. Okay, fair enough. All right. So one question is, if we enumerate substitution systems, I do want to mention one other thing because I realized just before this live stream actually a connection between machine learning and rule space, which is fun and is worth talking about. Okay, so we enumerate substitution systems. I'm looking for my convenient guide page of, hopefully this is it. Hopefully this is not an early version of it. Enumerate substitution system rules. Okay, so those should be, I'll make this bigger again. That should be our possible substitution system rules of size 2. Okay, so now how do we convert those to quantum operators?
So if we map multi-way to quantum system over that.
Okay.
And they're unsurprisingly a remarkably boring set of.
Right. So let's just understand. So there are a limited number of operators. These represent essentially the operators. They have different bases, but the operators may be the same here. Okay. So let's do the next case. So the next case will be we always have to. We could do 2 2 2 2. Correct.
Yeah, that's going to be more interesting. Slightly.
Okay, so now we've got a bunch of quantum operators. So let's go ahead and we don't really care about the bases. Is that a fair statement?
Unless we want to actually interpret them as string systems. Once we, the basis is what allows you to take the evolution and interpret it as a string substitution system.
Right. But these are just pure quantum. So if what we do here, just to get a sense of our quantum, what quantum operators did we just get here? And what kind of friendly gates did we get here? So first point is that everything will be non-negative integers. Everything we get out is non-negative integers.
Right.
Does that what does that mean to you? So because you'd had previously operators that didn't have just non-negative integers in them.
Right. But in the specification of the multi-way system rules, we can't have annihilation of states.
Yeah, so okay, but how do we interpret these as, okay, so if I just say, is that going to work? Yeah. Okay, so then I say like a little array plot for each of those, or matrix plot. Oh gosh, too big. Okay, so these are our Okay, so these are our quantum operators. Let me make them even much tinier than that. Okay, so those are the quantum operators associated with 2 goes to 2, 2 goes to 2 multi-way systems. Now, what can we learn from this? What is a, for example, we could find, is there a universal set of quantum operators here?
I'm trying to see if I can spot a C naught or something similar.
Well, tell me what the C naught is.
So it's a diagonal matrix, but with kind of one thing display. So it's like it would be it's a 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0.
It's a 4 by 4.
Yeah, because it's 2 qubits, one control, one operator.
Right. Yes. Okay.
So it's an identity matrix, but with the third and fourth rows swapped. And I don't immediately see one of those here.
Like that.
Right.
Okay.
Well, all of these have 2 ones,
Right, because we only have 2 rules.
Oh, I see. So to get this, we'd have to have 4 rules.
At least. They don't all have 2 ones. They have at most 2 ones.
Okay. So if we were to get, so one thing we could do is just find out how many, okay, so let's do this. Let's package it up a little bit. Okay, so this is multi-way to quantum. Can I request in the multi-way to quantum to just get the operators, or do I need to?
Unfortunately not. No, you need to get the whole association.
Operator there on that. And then I want to get, well, then that would just get me all the operators. Okay, so let's just say counts of those. Okay, so there are multiple ones that get a few of those operators. Okay, so let's do the corresponding case for let's do that case. Okay, so these are all of the ternary things, but here there are, oh, I see, there are size 4. They're 4-dimensional. What's the maximum dimension that you get here? Well, let's just do that. Let's say, let's count the dimensions here. Ah. Okay, so predominantly they're 4 by 4s. Okay, so this is just telling us from,
right. The maximum dimension is 4 because with 3 2 goes to 2 rules, you can have no more than 6 strings, 6 basis elements. Right.
Okay, so let's do this.
And 6 is less than or equal to 2 to the 3.
Okay, not very exciting. Okay, question on live stream from Anders. Are those quantum strings, superposition strings, interpreted as qubits? So these are the operators, right? So they have basis. These are operators.
Operators on the string basis.
Right. Okay. So what do we want to learn from this? What were you were asking? How big, for example, does the underlying multi-way system have to be to achieve a certain quantum operator? It's one question. We can compute that directly, but go ahead.
Yeah, how common are the interesting quantum operators in the space of interesting substitution systems, for instance?
What's an interesting quantum operator?
Well, for instance, the ones that have names.
Okay, well, what are the ones with names? Can you get me a list of the ones with names, and we'll just go find them?
Yeah, sure. I mean, hang on. There's probably a Wikipedia article about them, but
don't we have them in the
oh yeah, I mean, we could also
just scrape them from the quantum computation package.
Let me see if we ever got around to documenting all of the operators. I'm not sure if we did.
Well, but I mean, can't we just get them from the code?
We can, but there's a lot of them, and do you want me to systematically?
Well, let's look at the code. Let's look at the code. See if we can systematically scrape it from the code. Where is the code? Do I have the code? Is it in?
I mean, I emailed you a version of the package a while ago.
It's in code development.
Oh, there is that. Yeah.
Quantum framework. And then what? Quantum discrete vial, quantum discrete Vigna.
Quantum2.wl is the actual framework.
Okay. So what am I searching for here? If I search for C0, for example.
Well, hang on. This is all discrete state stuff. If you okay, you can just search for C0. Yeah, you want all the quantum discrete operator stuff down there.
I see. So quantum discrete operator, we need to know what are the possible first arguments to quantum discrete operator.
Right.
Those are all the quantum discrete. So if we could get that, which we don't seem to have, what matrix representation? Okay, so but the named ones are up here.
Yeah, and by the way, I make no claim that this list is exhaustive. These are just the ones I could easily find.
Okay. So one way to do that would be, oh my God, this is all in one cell. That's crazy. That's completely crazy. Why is this all in one cell?
Because it's all one function.
It is?
Quantum discrete operator.
Oh. Well.
Why would it not be in one cell? I don't know.
My programming
style is to use separate cells for separate functions.
Okay. Quantum discrete operator is that function, right?
Right.
Okay, I'm going to do something absolutely horrifying here. Let's look at the down values of quantum discrete operator. Max, do you know how to do this? I'm going to try to get all of the left-hand sides of quantum discrete operator. Do you know how to do that?
Well, you should get the rules now. So you could just take first of the rules.
There you go. Okay, so what we want to do is 1, 2. This is such a hack. I am ashamed of myself here. This is a deep hack. Okay, so if I do,
that's a correct way to parse Wolfram language.
Yeah, right. But so it's 1, 1, 1. It's 1, 1, 1. Okay. So let me go first as hash 1. And I'm going to be so unbelievably hacky. I'm going to say quiet here to stop getting all the messages from the things that don't have that structure. Okay. And now I'm going to say, this is such a hack. This is outrageous. Okay, I'm going to say cases in this of underscore string. Now, arguably, I could have typed it in less time than it took to do this, but anyway.
And also it missed most of them.
What do you mean it missed most of them?
Because most of them don't have that pattern. Most of them are infinite parametric families of operators that have list, the name, and then a parameter.
Oh, well, then I can get that too, right? I just have to go one level down, don't I?
Right.
No, that doesn't seem correct. Give me an example of one that does that, for which that's the case. But
C phase.
What's that?
Wait, no, hang on.
I don't believe that is the pattern because C phase has look. It has
no. Sorry, C phase is a bad example, but that is the trust me, that is the pattern.
Well, find one that has that pattern. Where?
Oh, right, that's right. I wrote defaults for all of them.
Okay, fine.
Yes, so you are still missing most of them.
What do you mean? Which ones am I missing?
Well, like things like C phase and Pauli and others for anything other than the default.
I see. I see. Okay, but fine. But these will give me. So if I say quantum discrete operator of line 334, how do I actually get that resolved?
You need an order. You need to specify wire positions.
So I need to say 1, 2, 3, for example.
For an arity 3 operator, but it will vary.
Sigh. Okay. Well, so this is a mess. Okay, so some of them have correct arity and some do not. Why has that got such a complicated discrete operator form?
What? No. Only the last two and the penultimate and one before it evaluated. All the rest were incorrect.
No, I know, but why is this such a big? Oh, arity 4 means 2 to the 16, 2 to the 4. Is that right?
Yeah.
I see. So it's a 16 by 16 matrix.
Right.
All right. So the question of where, the issue of where the named operators show up is a question that we should be able to answer.
Mm-hmm.
So of all possible substitution systems, how many correspond to named operators? Right. So, and it's a question we don't know the answer to, but clearly we can figure that out. Of possible substitution systems, I mean, I don't understand. In general, with quantum operators, it's just like enumerating integer matrices would give one an enumeration of possible. I mean, the mapping of those to substitution systems isn't clear, but that tells one the number of possible quantum operators.
Yeah, sure. No, I'm interested in what I want to figure out is how successful have quantum information people been in excavating the space of interesting quantum operators.
I understand.
Right. We have a way of addressing that because we can pick the substitution systems that have non-trivial behavior and see what their operator form is.
Well, that's a reasonable point. So, I mean, if I were to look at these, what would I want to look at? I want to look at the multi-way systems, presumably, for those, for these things here, right? I could look at the multi-way systems for these.
Right. And if any of them have interesting behavior, and they don't correspond to a known quantum operator, that's interesting.
Yeah, right. So then we should just say resource function of this with a multi-way system. That, comma, what should I start them with? Like AA or something? And then let's say 4 steps and then states graph. Actually, let me go ahead and let me go like 5 steps, but put a time constraint around them. Is there a time constraint option in multi-way system?
No, but I'm increasingly convinced I should add one.
Well, I mean, it's a common thing to want to do, but there's no reason to add it if it's just going to do. Okay, let me just use modern technology here.
Would it make your parallel stuff easier if the time constraint option was inside a multi-way system? Presumably not.
No, it doesn't make any difference.
Right.
I am going to be so happy when I've got a new way to launch my parallel kernels coming very soon using the persistent Wolfram WSTP server persistent Wolfram engine system, which should be much faster than this because this is actually doing SSH to launch kernels on different machines. I also will be so happy when this isn't a piece of ASCII art, so to speak, here. Okay. Oh, I should have help. Oh, I wrote time constraint, and I should have written time constrained, and I should also have written here states graph structure. And the answer is, and I should also have written in here graph that, let's make it quite tiny.
And you should use probably evolution graph structure, because the states graph is going to have at most 4 nodes in it.
Why do the evolution graphs always look so ugly?
Need to put image size before 4.
Thank you. Way before 4. I'm sorry, I've got that completely confused. Ah, bad idea. Boring.
There are a couple of interesting ones. Well, I use interesting relatively.
Let's try the next case up. And actually, what we should do is aggregate them before we display them. Oh gosh, it's gonna drive me crazy. How big is it? Let's not do it this way. There are some interesting ones here, but let's do it in a less stupid way. Let us do a counts on this. And actually, I probably could make the image size a bit bigger. Okay, here we go. All right, so what do you think you're going to see that you think will be interesting? Is that interesting? It's mildly interesting.
It's a bit classical.
In what's that it's very vertical. It doesn't fan out very much.
Yeah. That's not going to go.
Yeah, well, I mean, these are very classical here, right? I mean, these are
right.
This is pure classical.
No, but there's some like that one there that you enhanced before on the right.
Yes, that's mildly interesting.
That's pretty. Like, it'd be cool to see. Is that an operator that we recognize?
I'm sure the answer is no, just based
Right.
on the number of operators that are here. But I think it's also interesting to see what the level of non-classicality is to all of these things.
Yes, absolutely.
All right, let's just do the next level up.
Because I have a suspicion that, rather like your claim that, engineers tend to build things that they can readily foresee the consequences of, I have a suspicion that people who construct quantum gates have been constrained by having them be, very close to being classical.
Well, that's an interesting claim.
That actually most quantum operators don't make full use of branch yield space.
Well, you've got the explicit answer to that here. We can work out what the fan out is for all of these things, and what the buffing out is there. Oh, come on here. Oh, there we go. Wait a minute. Okay, let's look at some of these guys. I wonder if something has been made more dynamic in the because this is much slower to render. I wonder whether something in 12.1 has made some graph rendering thing dynamic that wasn't dynamic before. Look, there are some pretty interesting things here. Look at this.
Those are cool, yeah.
Wow, these are pretty interesting.
Yeah, there's a lot of zoology to do here.
Yeah, but the question is, right, so these are little partial. So what would a grid be? What would a grid mean if the thing built up a grid?
That's
it's some kind of pseudo-spatial.
Yeah.
Because in general, the thing could be a tree, but it's not in that case. In that case, it's an abelian. It's like a calligraph, an abelian group.
Right.
Yeah, so what does this mean here? That's something which has a 4-step merge.
That's something with apparent quantum advantage, but actual not quantum advantage.
Okay, so this is, so to understand what this is, so this is potential quantum gates. I mean, clearly you can just write down, I mean, okay, so this, we need to, yeah, I mean, in principle, you can just write down any quantum gate, just you'd give its operator. But this is saying if you want to actualize that in terms of a multi-way system, this is what, these are the quantum gates that you can actualize in terms of multi-way systems. What do you think the relationship to David Deutsch's constructor theory is? We have got to
well, so the obviously constructor theory is about defining physical transformations not in terms of equations of motion, but in terms of classes of permissible and not permissible tasks. Or so that's much more like a multi-way system specification. You're saying which states can and cannot be transformed into each other.
Yeah.
So
So I'm asking, is this an actualization of constructor theory in the sense that?
Absolutely.
Well, then we have to get. I need to. I think David was okay. We need to get him on one of these live streams, and we can send him this.
Actually, I suspect, you know, those causal connection graphs we were making for the black hole case.
Yes.
I suspect that one of those for the multi-way case is more directly analogous, because constructor theory is not primarily talking about, it's more about computability than it is about complexity. It's not talking about how many steps are needed in transformations. It's talking about which transformations can fundamentally be made to occur. So it's really a question about connectivity in the multi-way system.
Okay, so what you're saying is, what is the analog of event horizons in the multi-way system?
Exactly. That's saying, yeah, right.
So what is that in the quantum computing world? Okay, that's an interesting question, right? So boy, there's a lot of zoology there. Okay, so analog of event horizons in essentially branchial space / multi-way space. So what is an event horizon here? An event horizon is something that is a set of quantum states that you cannot reach. It's like a super selection sector.
Exactly.
So a simple event horizon is just a super selection rule. But super selection rules are not well studied in, at least back in, I'm so out of date, but I mean in they weren't, you know, it's just like there is a super selection sector, boom, there it is, rather than what's the boundary of the super selection region, so to speak.
Right.
But what this is telling us is there will be a set of quantum states that are, I mean, this is also disconnection in the branchial graph is another version of this. I mean, so, you know, I think that's related here. What is the relationship to disconnection in branchial graph? So actually what it is if it was the multi-step branchial graph, okay,
they would be the same. But if it's the single step branchial graph, that's like the spatial disconnection versus causal graph disconnection.
Yes.
Distinction.
This is, so disconnection in the branchial graph is
it implies event horizon, but not vice versa if it's a single step.
Wait a minute. You're saying
if it's a if it's a multi-step, yeah.
What this is saying is, as soon as there's disconnection in the branchial graph, that is saying that there is causal disconnection.
Right.
But you can always reach, in a multi-way graph, you can always reach, just like you can, you know, from the initialization event of the universe, you can reach every event.
Right.
Right. So this is saying, so disconnected components in the branchial graph correspond to different superselection sectors. So that's effectively saying, but I don't know the analog of the black hole case. I mean, that's simply saying what's connected and what's not connected. You Yeah,
Yeah,
there's clearly
right.
a what can you reach by doing what quantum operations.
We have a way of geometrizing super selection rules, which I don't think has really been done before.
Right. So let's think about that for a second. So what would be an example of a super selection rule and its operation in a quantum computer? Do super selection rules play a role in quantum computers? I don't know.
You can certainly use they're certainly used in the description of quantum information.
Is that right?
Mm-hmm.
See, I'm out of date, as you know. So how are they used there?
Well, so they're effectively they're used to define if your quantum computation starts from a particular state, then you can define a super selection rule that tells you what's the space of states that you're going to necessarily stay within, subject to your particular choice of gates.
Fair enough, yeah. But do people? I mean, that's to me that's like a debugging thing, right? It's like the validation of a quantum computer is, oh, you can't get yourself in that weird state where your computer blows up.
Exactly. So I've seen them in the proof of correctness of quantum algorithms and things, of saying like, okay, obviously if you end up in some state that's forbidden by the super selection rule, then something went wrong.
Okay, so super selection sector is like validation related. By the way, we need super selection as a spelling word. Let me just send that in before I forget. Oh, somebody already reported it. Good. Okay, so super selection sector is like validation, e.g. for a quantum circuit. Actually, it's interesting that super selection sector, like if you're doing combinators, if we're doing one of these things that we now know is related to a Bohm tree for combinators, if we're doing one of these multi-way graphs for combinators, in a sense, the connectivity of the branch yield graph for combinator multi-way systems would be a proof of correctness for combinators.
Yes. Right.
I mean, that's an interesting idea, the combinator branch yield graph.
Yes. And I like the general idea of geometrizing proofs of correctness. The idea that you can state proofs of correctness as in terms of the topology of branch yield space.
Yeah, I understand.
Is pretty cool.
Right. So
I don't know if it's geometrization or if it's topologization, because it's really just
it's really geometrization, because you have a metric. I mean, you can also ask questions like, even if you know that it's connected, it might be a long way away.
Right. It's the computability theory is the topology, and the complexity theory is the geometry, I think.
Indeed, I think that's correct. Yes. No, I agree that the computability is topology. Computability is topology of multi-way, of branch yield space, actually rule space, and computational complexity is geometry. Okay, that leads me to, I have to show one thing I was just looking at. So in rule space, let's see where this is. Wrong place. I think I was showing before. I'm not sure if I showed these, but these were my all possible non-deterministic Turing machines. So for people who are the idea of rule space is that in addition to there being different ways to apply a given rule at a given step in the multi-way system, you also consider all possible rules to apply. So in general, with a non-deterministic Turing machine, you can just take, so if we imagine a Turing machine where we have...
You're not using my my non-deterministic Turing machine rendering functions.
Well, that's because I wrote this before I had those. So let's use those. Hold on, let's use those. Where are those?
So I think that I think I put them in Dropbox. Let me just double check.
I think I wrote this a couple of weeks ago before those existed.
Okay, that explains it.
Are they in code development?
Yeah, they'll be in code. I think they're in code development drafts somewhere.
I don't see a code development drafts. I see a JG finalized.
No, no, it's hang on. Is it code development, function repository, sources, JG drafts?
Okay.
They're in there. Yeah.
Multiway Turing machines.
Yep,
Okay, cool.
that's the one.
Okay. All right, so let me evaluate that. And now let me just make this file here, Rulial 03 non-deterministic Turing machines. Oh gosh, are we getting this ridiculous finder bug here where it takes forever to put that? That's really odd. You know, we should report, somebody should look at this. I think it has something to do with some dynamics that are being used in graph rendering. Thank you. Okay. So how do I use your non-deterministic Turing machine?
So you just call multi-way Turing machine, and then you pass in a list of Turing machine IDs, and then just the initial condition step count.
Okay.
All the arguments should be the same.
Wait. So it's resource function of multi-way system.
No. It calls multi-way system. So you can just call multi-way Turing machine, and it takes the standard multi-way system arguments.
But it takes its first argument.
But the rule is a list of Turing machines, Turing machine IDs.
Okay, there are a list of Turing machine IDs. And what initial conditions? So I've got an initial condition here that I've been using for the Turing machines.
Okay.
And then, yeah, this one should give that same.
One would hope.
Oh, I see. You are not allowing a non-deterministic initial condition. I think that's a bug. In other words, you're requiring a specific initial condition.
Hang on, am I doing that? Wait, let me see. Oh, yeah, so I am. That is a bug.
Okay, all right. Let's see, what do I say? Vertex size. Oh, little Turing machines. What are those little Turing machines?
So that's an array plot of the internal state at the top and an array plot of the tape at the bottom.
How do I read the internal states?
I mean, what it's just array plotting the 110, for instance.
What is the one? Wait a minute. The 110
is whatever it is. I forget the ordering now, but it's the tape. It's the internal state, the tape position, and the orientation.
I see. So actually, it'd be better to plot that on the tape here.
Yes, yeah, as a graphic.
But yeah, we could do that with rule plot.
Right.
Okay, so the more interesting case here. Let me show you this. This is a much wilder animal. This is Turing machine. So there are 4,096 possible Turing machines. All right, let's do this. This is probably going to be rather horrifying, but let's. Oh, didn't even take very long. All right, let's make that size 5, for example. Okay, so this represents Rulial space, basically. That's representing each arrow. So can we put events in here? Do you have events?
Yeah. Yep, it's all working.
Okay, evolution events graph, right?
Right. You can even do causal graph if you want to.
I will. Wow. Okay. Okay. So those are lots of little Turing machines. Wow. It's quite wild. So this is basically representing, let's try doing vertex size 10. So each one of those is a Turing machine, is a oh, great. Wow. That's topologically quite interesting. Okay, so each one of these is a transition function for a Turing machine, right?
Right.
And this is representing the transitions between states in Rulial space. So one thing we could do, I think I did it down here, was I'm looking at all 4,096 Turing machines of this type. And now, okay, so let's just do that. Just for fun, how many did I do there? I did 3. Let's do 3 steps there. And let's do states graph structure. Forget that. And right, so that should reproduce that picture. Let's just do it for 2 steps. And then I'm going to talk about machine learning here in a second, because what I want to talk about is what the continuum limit of this rulal graph actually is. Okay, so that shows the different possible states. So those are probably a limited number. If I do a vertex list here, a length of vertex list, that's probably just the number of distinct outputs. It's interesting. I don't know why that would be the case, but that's the number of distinct outputs that I can get from those Turing machines, right?
Right.
Okay, so let's talk about the continuum limit of this, right? It gets very, very wild. Actually, I'm sorry, I'm addicted to finding out what the causal graph looks like for this. This could be very, very, very wild and crazy. Oh my gosh, for 2 steps, it's really taking this long? Well, that's what you get, I suppose, for having 4,096 possible rules. I mean, this is surprisingly civilized.
Yeah. It kind of shows you how much limitation there is in what Turing machines can do.
Indeed. I mean, there's a map of all possible non-deterministic Turing machine activity. So this is telling you for an NP complete, an NP problem, this is showing you what non-determinism buys you.
Right.
Because any deterministic Turing machine path is a specific path through here. But this is the aggregate of all non-determinism.
Right.
And this is not coming back. Let's just try doing a smaller one. Oh, piffle. That's what I had wrong. Well, let's just try anyway. Let's do our 2000 to 2000 and whatever it was.
That's probably part of the problem, but there may be something else going wrong.
Okay, that wasn't so bad. That will have been a serious problem. Okay, let's try doing that. Okay, so this is going to be a causal graph of representing the relationship between steps in all possible Turing machines non-deterministically. Let's see. Okay, Nicholas is asking what determines the distance and orientation between nodes on these graphs. They're basically just for visualization. I mean, in other words, the only thing that really is significant is the collectivity of the graph. But it is interesting. I mean, the high degree of symmetry here, which obviously we've successfully detected, is a sign of symmetries among the Turing machines. This is all possible 2-state, 2-color Turing machines. And this shows that there's obviously symmetry because, the Turing machine probably has mirror symmetry, it has 1-0 reversal symmetry, etc. And this is a bit scary. Let's try. Let's just try. I'll kill it. And let's just try going up to like 100. Boring. Okay, let's try going from. See, I wish I knew a subset of the Turing machines that was going to be more interesting. I mean, let's say going up to 500. I mean, this is obviously there's a 500 squared operations at least that it has to compute.
Right.
And yeah, I mean, this is probably going to be some very wild animal. But I would like to get a subset of the Turing machines that are reasonable to look at. By the way, did you get the Combinator one of these working or not?
Yep. Yeah. That's also in there in
Okay.
JG drafts.
Okay.
Causal networks for combinators are pretty fun. I've discovered they look quite different from many other causal graphs we've seen.
Okay, well, we'll look at them in a second. What about branch hill graphs for these things?
Oh, I haven't looked at those. I mean, we can plot them obviously, but
why is this taking forever? I mean, how difficult can a two Turing machine running for 2 steps be? All right, let's try 200 Turing machines.
Yeah, but doing 500 of them and then finding causal connections between the other 499 is a bit tricky.
Okay, why are these so disconnected?
Well, it's telling you that there are only 4 initial events that are possible, 4 separate initial events that can happen.
Yes.
And then each
then
of
they
those
just don't.
4, yeah, and then the events for those 4 classes don't happen to reconverge. We could find out. I mean, we could run it for a few more steps and see if they do.
Well, I'm pretty sure that in general, if you run all 4096 Turing machines, they will reconverge.
Right. Well, your state space is decidedly finite. No, but I mean,
no. But the whole point is that every Turing machine has an inverse Turing machine within that set.
Right. But I'm just curious. But I mean, what happens if we run it for more than 2 steps? 2 steps is a bit.
I think it'll take forever. Oops. I think it'll simply take forever.
Okay, but then don't run all 200. Run, whatever it was above that gave you those.
Maybe that was just 50 Turing machines. I remember. Oh, there we go. Oh, becoming more exciting.
Yeah, there's not much to see. I mean, causal graphs are pretty boring for just 2 steps in most, at the best of times.
Why is it making a ladder-like thing? Okay, so the speculation would be maybe it's a finite dimensional object that you get out. I mean, what is the limit in Turing space, so to speak, of, for example, the states graph? What is its limit in Turing space?
Right.
So this particular thing, oops, we continue at another step. Actually, what I did before, which was helpful, was making simple graph from this, because not caring that we have multiple connections here. And I think if we do 3 steps here, and I don't know whether it may matter. I'm now very curious what the branch hill graph structure of this is.
By the way, it's pretty amusing to have 36 as your upper bound for the degree to which P and NP can be related.
It is.
That's a nice upper bound.
Right. I mean, yeah, I mean, because what will happen here is NP, I mean, very much like in the quantum computing case, the P versus N, oh, look at that. Wow. This is cool. That is an interesting object. Someone's asking, how does a multiway Turing machine differ from non-deterministic? What this is showing is all possible Turing machine rules. So each path is a particular choice of non-deterministic, a particular selection of non-determinism in the Turing machine. So and a particular Turing machine uses only certain arrows. A particular deterministic Turing machine would use only certain arrows in this picture. Okay, I have to do the 4-state case. And I wonder what happens if I just take, let's just see what happens if I do simple graph on %377. Oh, it doesn't do anything. What happens if I do simple graph of undirected graph?
Interesting, yeah.
It's also not very exciting. Oh, what happens if I do, I see. So what I've got is I've got clusters here that are forming for reasons I don't fully understand. Those may be clusters that have similar tape configurations or something. All right, let's try the 4 case. I wonder whether, did I do this before? Maybe I did that before. Oh, I already did branch hill graphs. Huh. Yeah, okay. Well, let's just try this. So what does it mean that the branchial space is disconnected?
It means there are Turing machine superselection sectors.
Yes. And what does that mean in terms of what that means is, what the heck does that mean? Well, let me tell you my analogy with machine learning while it's doing this, okay? So imagine we're trying to take the continuum limit of this, okay? Imagine instead of a Turing machine step, we take one operation, one iteration of a neural network. So we're just doing one, matrix operation, so to speak, one matrix operation and gosh, what is it called? The ramp or something function. You know what I'm saying? Oh gosh, what is that called?
Yeah, the nonlinear feedback thing you do in
the
neural
nonlinearity plus yeah, by the way, Freeman is on our live stream is pointing out that the branchial disconnection is the failure to be able, but it isn't quite the failure to be able to reach states. It's the failure of two.
It's saying once you're in a region, you can't then get out.
That no Turing machine, no single step change of your Turing machine rule gets you to a different region. Up. Look at that. Never before seen object. Wow. What does that mean? What is the limit? What is the limit of this going to be? I mean, this is the space.
It looks hyperbolic.
Well, it better be causal invariant, which it looks very much like it could be.
Well, we can test.
All right, let's test it. Okay, let's just at least test the two-step case. So what is it? Causal invariant Q?
Yep.
How many steps does it have to run to check causal invariance for two? It's just running
4.
That's going to take as long as this one did. Okay, let me talk about machine learning. Wow, this is an interesting object. It's a very interesting object. It's the space of ta-da.
Hey.
I thought it had. I mean, it has to be true. Has to be.
It'd be an interesting proof of the existence of hypercomputers.
What? That a Turing machine the
proving that NDTMs are not causal invariant, I think, is equivalent to a proof that you can construct a hypercomputer.
I don't see that immediately, but
because you're saying that there are GD6 in the rulal space of Turing machines that don't converge.
Oh, I see. Funky. Okay, so this is right. You're saying that there are places you can't reach. There's an event horizon. I mean, is there? Okay, so another question is there? So what we're seeing here is there are effectively event horizons here.
Yeah, but they're presumably very local.
Indeed,
they're locally existent, trapped surfaces, branchial trapped surfaces.
What the heck does that mean? So what that means is there are parts of Turing machine space that are hard to get out of.
Yeah, they're your local minima in your machine learning continuum limit, probably.
Maybe. But they're hard to get out of. You've gotten in there by some Turing machines, and it's tough to find Turing machines that get you out of that region of rulal space. What does that mean? Okay, let me explain the machine learning analog. Okay, so imagine that every edge here is a neural net operator, and imagine every state here is the state of the neural net. Okay, So when you do a classification problem, you are basically saying, you're starting from some region in the neural net, and you're saying you want to, there's a bundle of GD6 that are the things that will look like a dog, for example. And your goal is to have all those GD6 concentrate down into a sort of a single black hole that represents the dog output, right? And another set of GD6 over here, you want to concentrate those down to a single black hole effectively that represents the cat output. Does that make sense?
Yeah, yeah.
So the question is, what's the analog of Einstein's equations in machine learning limit of this setup? So remember, what's happening here is every evaluation, every path through this graph corresponds to an evaluation, a neural net evaluation, right? And every possible path is evaluation of a different neural net with a different series of layers, right? And so what we're asking is, we want to find, we're trying to select a path. What we're trying to do, it's like in general relativity, if you want to travel to the outer solar system, you have to wait until the planets are lined up in a particular way so that your spacecraft can be sort of, sort of catapulted towards Pluto or whatever, right? So similarly here, what you have to do is you have to find a path, find a set of these edges that will successfully take your bundle of inputs that corresponds to cats and take them to the, to the cat black hole, so to speak, I think.
Uh-huh.
And so the question is, what's the analog of Einstein's equations for this, in this case? What's the analog of GD6? What's the analog of curvature? What is the curvature of neural net space effectively? What's the curvature of the machine learning space? And that's asking, given that you have two GD6, you're looking at GD6 in different orders. I have no idea what that is. I mean, so that's asking for two neural nets that you apply in two different orders. That's a thing we can easily answer. So this is, I'm just going to make separate notes about this. So this is the continuum limit of Rulliel space.
It's a continuum limit.
Why are you making that? I mean, you mean because neural nets aren't the whole story of how you can parameterize computation.
Right. The neural networks are one coordinatization, and in
Indeed.
my rather biased opinion, I don't think they're a particularly good one.
Well, fair enough. But okay, so the question is, what is the analog? Okay, so let's say neural nets as a continuum approximation, as a continuum coordinatization of Rulliel space. Coordinatization. I spelled that correctly. We need both of those things as spelling words. Okay, so what we're saying here is, okay, so the first question is, what is curvature? Okay, so curvature is a failure to commute of a neural net operator.
Or a sequence of neural net operators.
Right. But I mean, we could take a typical neural net operator. What is it called? Linear layer? Yeah, linear layer. There we go. So we could pick a linear layer, and then we could just say, I do not know. Let's take a look how this works. We have to train it. Oh God, what a horrible mess. We got to train it on MNIST digits to get a viable linear layer. We can train it on an infinitesimally different. Let's remind ourselves how linear layer works. Okay. Yeah, so it needs a weight vector. So we can just say net initialize, and we'll get a random initialization. Oh, why not? Maybe we need an input layer. We need to know the input. Anybody here, Max, do you know how to do this?
No, not really.
we might need a different. Oh, look. Let's see. A linear layer, ramp, a linear layer. What happens if I just do this? No, I need to be telling it a little bit more stuff. But so the question would be, how do I get I can actually visualize what happens when two layers will not commute in general. What does their non-commutation mean? There's a question of, can you get, if you take two different paths in weight space, I mean, I suspect it has something to do with training. I suspect that the curvature has something to do with the, whether gradient descent can work and things like this. We should get machine learning people here if we really want an answer to this. I wonder whether maybe we could see if Etienne might be available just briefly. We should do this another time. But we'll find out if he's available. Okay, but in any case, the concept here would be, okay, again, okay, so first question is, what is the analog of curvature? What is the significance of curvature? Next question is, what's the analog of energy momentum in this neural net space? And I think we were talking about this earlier with the machine learning group, actually. And analog of energy momentum may be training data. Because what it's doing is the energy momentum, I mean, the presence of energy momentum is turning these geodesics. And that's basically determining, how they, I don't know, it's positive energy momentum is converging geodesics, right? It's what it does by the way, what is the analog of positive energy momentum in the Lagrangian density in the quantum path integral? I don't know what a positive Lagrangian density really means. I've never really thought about the sign of Lagrangian density. One never considers that. Although maybe it's related, again, sorry, we're skipping to completely different domains of isn't the effective potential, this might be a question Max might know, he might be more recently having studied this than I have. The effective potential corresponds to is gotten from the Lagrangian density. So I think it may be that is what, but anyway, okay, never mind. Yeah, maybe we should wrap up soon here, and maybe we should schedule another time to talk about the relationship between machine learning and rule space. It's amazing how much kind of unification of all these different fields is in the offing here. I mean, is there any other continuum limit that we can think of? The only continuum
microfluidics.
What do you mean? You mean turning gates into microfluidic gates?
The analog, the continuum limit of quantum operators, I suspect is or can be represented as microfluidics.
What is the microfluidic analog of an OR gate?
Well, an OR gate is not reversible.
Okay, so all right, so you're saying microfluidics as an alternative continuum limit.
Right. So anything that you can represent as a quantum, as a unitary evolution, you can represent using microfluidics because they have to be reversible.
I know.
So an OR gate.
But they also have conservation of fluid. which is a different thing. Reversibility
Yes.
does not require conservation of fluid.
No, it doesn't. Well, reversibility also doesn't require conservation of measure.
Indeed.
So which is why I'm saying I think it's analogous to the quantum computing case. So I think
So what are the microfluidic gates?
Well, they're things like C naught, C or those kinds of things.
Can we just get but they should have a continuum value. Let's see.
So my point is that when you conventionally build a microfluidic object, right, you're using it to implement a classical logic gate.
Oh, I know.
So people only consider the discrete case, but they're obviously they're actually continuous.
Well, I don't necessarily believe you. I mean, in other words, you're saying that what's a C naught gate? What is it? So what's the minimum? What's the minimum gate that we can consider? Because what you're going to claim is that we can make those operators that you were previously showing as integer matrices, that we can make them non-integer matrices, right?
Right, or that you could have you could still have them be integer matrices, but where the exponent is a real number.
You mean, well, okay, where the exponent of the matrix power is a real number.
Yes.
That's a different thing. That's continuous time. That's not continuous variation of, look, what you're saying is, can we take an example here? That what you're basically saying, okay, another alternative continuum mode with continuum cellular automata. Continuous cellular automata.
Sure.
I mean, that's a more obvious continuum limit here. Actually, that's a case we should look at. Freeman is complaining that the documentation for multi-way Turing machine is not in the repository yet. That's because it's still just a draft.
I will be submitting it to the function repository in the next 2 days.
Okay, so
and then it's in their hands.
Yeah, then it will show up there. Sorry, not yet there. Okay, but let's think about the continuous cellular automaton case as an alternative here. I mean, so what we're talking about in that case is, a typical continuous cellular automaton, to remind ourselves of how that works, is our friendly, where is it? Continuous cellular automata was a good place to start. Okay, it's something where we have a ramp function. This is like a convolutional neural net, actually. So that's a typical case, fractional part of 3/2. So that would be a rotate left. What am I doing here? I'm doing a block map of total, I think, onto, let's look up how block map works. N, right, of total onto, let's say, center list, center array of 10 of 1, 10, comma, let's say 3. Okay, right. So that will take, what is that doing? Block map should take center array of this, should make an array like this. Okay, now block map should be evaluating those things, right? Evaluating those bytes of the center array, if I'm not mistaken. If I say block map of F center array 3, yeah, what happened in that first case?
That's correct.
These are the totals.
It's doing the totals, yeah.
Yeah, right. Because I didn't, but block map is not, oh, silly me, I need an overlap criterion there. That's the correct answer, right? Okay, so then what I want to do for the continuous cellular automaton is I'm just saying that block map, and then onto that I say fractional part of 3/2 times that. And that should give me that. And now all I have to do is say this with a hash. And if I'm lucky, I don't actually know whether this is going to work because I don't know about the end conditions. A nest list of that, comma 10. Oh, drat. I wonder whether block map has a way of doing that. It's kind of annoying. Okay, well I can clearly do this as an alternative. I can just say rotate left of a bit annoying here. I have to do the rotate left of state s hash / at -101 if I want those combined, and then I would say total of that, I think, and then that's the state function s, and then I could say like fractional part. Let's just do fractional part 3/2 that. And then hopefully I can now say nest list of center array this, comma 5 or something. Okay, great. Okay, so that should produce for me the, I mean, it's ugly how those things get. I mean, notice that it's really using real numberism, so to speak, here. So if I go, let's say 50 here, and then I go 50 steps here. Actually, I need to do 100 there if I'm going to do 50 steps. And then I say array plot, then I should get a picture like that. Great. Why does that look different from the picture in the NKS book? Maybe it doesn't. No, why does it look different? Gray level of each cell. Why is that different there? Half, half, half. 0.25, 0.25. Why is that different? Look, it's 0.25, 0.5, 0.75. Am I doing this wrong? I'm taking the total. Maybe it's doing some weird transpose there.
Right, it's almost like you should flip the things symmetrically.
Maybe this is the right thing. Oops. Total / at that. I need to get rid of that.
That looks less convincing.
That's totally wrong. What am I doing wrong here? Okay, so each thing, it's rotating left, rotating right. Why does it end up with this? It's taking this object. Okay, let's look at that piece of code there. And this was only a precursor to something else. So let's take this and okay, now by doing total on that, I should be combining this case. What's going wrong? And that's yet a different answer because that's combining. Well, let me just see what happens if I get rid of the fractional part. The fractional part is going to be necessary, right? Because otherwise the numbers are just going to get too big. Oh gosh. All right. Well, this is messed up, but help. Let's say 1/3 or something. Okay, that's a nice diffusion equation. That's about right. So let's say I say 0.95. Oh, wow. Let's say I say 0.9. Oh, what's going on here? 0.6. I'm a little confused. I mean, let's say I say 1.5 here. Am I doing something wrong? Fractional part of 3/2 x. Oh, the average gray level. Average gray level. Average, average, average. That's not total, that's mean. See what I'm saying? So the average would be this divided by 3. Ta-da! There we get the right result. Okay, so then let's say we do it for, let's say we do 200 of those for 300 steps. Beautiful. Okay, so there's our continuous cellular automaton.
Right, but so there are actually two continuum limits that we have to consider, which are inequivalent. There's the continuum limit in the space of states, and then there's the continuum limit in the set of possible outputs given a particular state.
Well, there's a continuum limit in the set of possible rules. I mean, so in this case, what we've got here, we can consider neighboring, if we have a non-deterministic cellular automaton, we can consider that the neighboring strands have the value of this parameter being slightly different.
Right. So this is a specification of an infinite family of rules, effectively.
Mm-hmm.
So that's one continuum limit because it defines an infinite set of states. I'm saying there's a different continuum limit, which is not the one produced in the CA case, but is the one produced in the neural net case, which is if you tried to produce a multi-way continuum CA, you would still get only finitely many states on each step. Right.
Why? I mean, if you've got an infinite number of rules, you get an infinite number of results.
But only... I don't understand. Your neighborhood structure is countable here.
Indeed.
So you have only finitely many possible outputs given an input.
No, you don't, because the rule has an arbitrary real number parameter in it.
Yes.
So as you change that real number parameter, you have an uncountable number of possible outputs. I think. And I mean, the neural net case, honestly, this is not that different from a convolutional neural net. I mean, it basically is a convolutional neural net.
Right. But my point is the reason why you get branching in for, say, a multi-way cellular automaton is because of the neighborhood structure.
Oh, you're saying, wait a minute, you're saying that because I see that the number of, no, but I think it's much worse than that in this case, because every cell has a continuous collection of possible values.
What? Why?
See,
every cell has an arbitrary real number value.
Exactly.
Yes.
That's called a continuous set of possible values.
No, but the cell only has one value. It doesn't have a set of possible values. I mean,
no, but as you change the rule, you change the set of possible values.
Yes, no, I understand. But my point is,
I have another idea.
There's still one level of finiteness that you haven't got rid of. You're missing one limit. In this.
Well, you're saying that neural nets, you can have yet another limit, which is the size of the matrices. I mean, you make graphons rather than graphs in some sense. The size of the matrix.
I don't know enough about the neural net case to know the correspondence. I'm just saying that there is a different continuum limit.
Yeah, there's an additional limit, which is the size of the cellular automaton neighborhood, aka the number of the size of the matrix and the
because this is still a surjective function.
Why do you think it's subjective? I mean, this is
given a state of a cell, or given the state of a neighborhood. It's the neighborhood on the next step is completely determined.
Sure. So is it?
Right. And because the neighborhood is only a von Neumann neighborhood, if you're given a multi-way version of that, you only have 3 possible outputs at most.
I understand what you're saying. Yeah, I understand what you're saying. So I mean, in this form, that's the state transition graph.
Your geodesics are still locally countable. which means that you don't get the full rich geometry that you would otherwise get in a true continuum limit of Rullial space, either with this or, as it sounds like, with neural nets.
I partially agree.
What you would need is a continuum multi-way system. I'm just thinking about a potential way of doing that.
Well, there are plenty of multi-way systems you can make with arithmetic. So in other words, we could make a multi-way system that, I think I had some examples in the NKS book of that. But I mean, so the other question is, for a continuum cellular automaton, for a continuous cellular automaton, what is its state transition graph like?
Right. And my point is that that graph is still continuous. Sorry, it's still countable, sorry, even though the individual states are continuous.
It's, well, in the sense that it has a discrete. Well, okay, so let me look. Actually, I had in the NKS book, I had numerical multi-way systems someplace. How much do you bet this is a note? Multi-dimensional multi-way systems. What the heck is that? What is that? Oh, this is instead of operating on 1D strings. Multi-way systems based on numbers. There we go. Okay, so consider the rule n goes to n plus 1 times 2n. So that's just asking at every step, take hash plus 1 and 2 times hash. So clearly we can change those numbers. So we can arbitrarily, we can say at every step, the general version of this will be a times hash plus b, a1 times hash plus b1, a2 times hash plus b2.
Mm-hmm. Right.
Okay, so then this is cool, actually. This is a cool object. Okay, so this is otherwise known as something very much like it's either like a Julia set or like one of my tree sets.
Right. So my argument is, what we need to also consider is the case of a multi-way system where the current layer is not a discrete collection of points, but rather an interval, a continuous interval.
Okay, you know what this is related to? This is related to our friend Bernat's giant study of trees. Let us see whether Bernat has his.
And we can easily implement this, right? Because we can implement a sprinkling scheme. We can implement a continuous multi-way system which produces a discrete approximation by a sprinkling procedure.
I didn't understand that, but let me just look at this for a second. This is
also, if you have a generalization of a multi-way system in which every state layer is an uncountable set, then you can construct discrete approximation. Then that set has a measure, and you can construct a discrete approximation by a sort of Poisson process, like we were talking about in the causal set case.
I need to understand that. This is relevant, however. This is the parameter space set of trees that are constructed by taking arbitrary. So this was this construction that I had in the NKS book except Bernat managed to figure out how to do this in a more efficient way than I'd ever figured out. Where essentially what you're doing is at every step, this is in the complex plane, but it doesn't really matter. You see what you're doing here? You're taking every result and you're generating it in you're generating a tree based on that.
Mm-hmm. Right. Yeah, I read the paper, but I mean the trees are still discrete objects.
I understand, but I'm trying to. Okay, so first point is this is related to Bernat's trees, so what is that saying? So that is saying that his trees correspond to an example, a somewhat continuous generalization of multi-way systems gosh, I had never noticed that connection before. That is so embarrassing. I had those trees in the NKS book, and I never noticed that they're the same as continuous multiway systems.
In what sense?
Well, they're the same thing. I mean,
In what
it's
sense?
because each one, each branch of the tree corresponds to some sequence of operations on these numbers.
Mm-hmm.
And then the question is whether this question about convergence of these trees, which is what we looked at in terms of connectivity of these trees, that's some kind of statement about. I mean, it's a causal invariance like statement.
Yeah, sure, but they're still discrete multiway systems.
Yes, I understand.
The state space is continuous, but the multiway system is not.
Okay, fine. So then what you want to define, okay, so this is, and then tree convergence is related to causal invariance. Okay, but now you want to define, Jonathan wants to define a fully continuous. Okay, fully continuous multiway systems. So that means that you don't have discrete steps. What the heck is that object?
No, you can still have discrete. There are many different layers of them. Look, my point is here that the fact that your state space is infinite doesn't really matter, because your state space is infinite for the hypergraph case, right?
Sure.
So your multi-way system for any finite length run isn't going to look any different. So you could consider continuous time, but as a step towards that, you could also consider continuous branchial space.
But isn't that what we're doing here? I mean, because we have continuous variables. Look, the numbers here that we have are continuous variables.
Mm-hmm. Right, but your functions are still surjective.
Which functions?
The evolution functions. What you need are evolution functions. What you need are multi-functions, right? That have such that for any input, the output is a continuous structure.
Your claim is that the fact that for example, in these trees, one thing goes in, two things come out, is not adequate. That I have to be able to have 1.87 things coming out.
Not 1.87 things. No, I mean that you have to have an uncountable. You are restricting yourselves to functions that operate such that for any element, a countable set of elements comes out. Multifunctions that have that property.
Sure.
In order for you to have locally continuous geodesics, what you need are multifunctions such that uncountable sets can come out.
If you really want continuous geodesics, why don't you need continuous time as well?
Well, no, you do. I mean, in addition to that, but I'm saying that there's an intermediate.
What is the mathematical object that is a continuous time, continuous states multiway system? What is it? I mean, clearly when we have non-multiing, when we have just functions as opposed to multifunctions, we're limiting to PDEs.
Right.
What is the thing? I suspect it's one of these things of the type that you see in path integrals, quantum field theory, one of these other places where you get, and I don't know enough about these, the whole world of C-star algebraism and so on to know, but you get what I'm saying. That what you're doing.
It's a generalization of some infinite dimensional function space or continuous dimensional function space story.
Yes, but that's a very complicated thing. So that's saying that, I mean, in other words, a PDE. So PDE is continuous states. Well, continuous states and time, but one-to-one functions basically. Whereas what you're asking for, and then the next case is we could consider one to countable functions, right? Another case is continuous states and time, but one to basically k functions.
And actually, that's an interesting question of whether, if you have continuous time, does it actually make any difference? Whether it's...
Yes, I understand the issue.
In fact, I'd rather my intuition says it probably doesn't make any
It
difference.
probably doesn't make a lot of difference. And I suspect
yeah.
by the time you've got continuous time, this is extremely awkward to have that number be anything other than 0.
Right. But yeah, there's some interesting measure theory to be done here.
What kind of an object is this? I mean, so in other words, in a PDE, you've got, so I think it's some kind of path integral-like thing.
Mm-hmm.
Which actually, at some level, is utterly unsurprising, because in our world, the multiway system, I mean, we should have known that from the beginning. The multiway system is supposed to limit to a path integral.
Mm-hmm.
So we're just saying the continuous generalization is a path integral.
Yeah.
Which doesn't really get us anywhere, because the mathematical state of studying path integrals is still, like most mathematicians think path integrals are kind of improper objects, even after years.
They are. I mean, you can't define a well-defined integral. You can't define a serious integration measure on a continuous dimensional function space.
Yeah.
That's still an open problem.
Well, I wonder, so our limiting case, anyway, I think it's a nice fact that the different case that is not continuous time, the fact that these relate to these, these trees is really quite interesting, and I hadn't really noticed that before. That's a continuous generalization of multiway systems. Somebody's suggesting like a PDE, but using algebraic loops instead of differentiators. One of these things is like that. Yeah. Well, very interesting stuff. All right. Well, so maybe another time we should discuss. We should discuss. I think what we need. Okay. We need machine learning people, and we need some mathematicians, more mathematicians, to discuss this. And I think we might discuss categorification sometime soon, which is yet a different form of abstraction here.
Probably not that different, because the arguably the most promising approach to axiomatizing continuous dimensional function spaces is treating them as compact dagger categories.
Whatever the hell that means. What is a dagger category?
They're a way of categorifying sort of C-star algebras, von Neumann algebras, those kinds of things.
This term categorifying, I still bothers me every time I hear it. I mean, it's like when people always used to say we're quantizing this or that. It's always very hard to know. I mean, actually, it reminds me in the technology space of people saying, what is the right term? Well, containerizing at least has a more direct meaning in software engineering. But there's another one of these that's in business speak, and I'm now forgetting it. How could I? It's another one of these terms that reminds me of quantizing or categorifying. It's another one of these things where basically what you're doing is, I mean, what those words mean is you're taking some system and you have a framework in mind, and you're finding a way to talk about that system in terms of that framework. But anyway, I hope to understand more about what categorification means. All right, well, lots of interesting things here. We should probably wrap it up and continue another time. Now, I think tomorrow, what is happening tomorrow? I'm signed up to do another science and technology Q&A for kids, and I don't know, probably on the subject again, because it was going so well before, of what in science fiction can be real, and see what other weird questions come up, and see how many other things end up being things that can be thought about in terms of our physics project. All right, well, thanks a lot, everybody, and thanks to folks on the live stream, and we'll be back another time. See you later.